laser pointer. Okay, can you see the laser pointer?
Yes.
Mm-hmm.
Hello, everyone. So today I would like to tell you, and I would like to thank first of all the organizer for the opportunity to tell you about this. Oops, okay, about this new idea that we have, how to produce topological superconductivity with Majoranas at the end of the carbon nanotube. And the main advantage will be that we need really small magnetic flux in order to produce these Majoranas. We estimate about 50 millitesla. The work was done by two students, Omri Lesser and Gal Shavit. They did all the work. I'm just telling about here today about their work. So I'm going to give a very brief history of these Majoranas, and it's not a full, all the discussions here about Majoranas. So I just want to highlight a few points which are important for the discussion today. So initially, Majoranas, we all know that were discussed in quantum Hall effect and in 2 dimensions. Then there were these ideas of the wires and experiment in indium antimony. Then there were many breakthroughs. I just want to mention the ones which are relevant for here. The epitaxial growth was really important to make the gap very hard. There are discussions of selective area growth. And what it was important for me, or for the discussion today, was this idea that you can use phases of the superconductor in order to, in these 2 experiments on the Josephson effect, on the Josephson junction, was shown that when you use the phases of the superconductor, you can make the required magnetic field to form a topological state smaller. And then there was this experiment, and we heard few talks in this conference about this full shell experiments in which a wire is covered totally by a superconductor, and the magnetic flux through the wire is drive the system into a superconducting, in a topological superconducting state. And the main thing here was that it's really the orbital effect which is important, and less the Zeeman effect. That was really important to understand that, in fact, Zeeman field, of course, will be there, but the main thing is just due to orbital effect. And that opened up many new opportunities. And there is another thing which I think is new concept. It was actually discussed initially, the idea to form both ferromagnetism and superconductivity. But this, I think, was the first experiment that shows that it was possible to do so using exchange field coming from the European sulfide and aluminum. This is in this experiment, and we'll hear more about that later on. So if you want, there are many reviews about that. I just want to highlight. So I pick one each year. So this is 2017. There is one in 2018, 2019, 2020. There are many reviews. You can read more about the progress, the real progress in the field. I just highlighted the fact that you can use orbital field in order to produce topological superconductivity, and that's what we will emphasize today. That when we put a magnetic field through the carbon nanotube, the main effect will be an orbital effect, although there is Zeeman field there, but it's not necessary. The main thing will be orbital effect. As usual, the three things that we need to produce topological superconductivity is spin orbit coupling, superconductivity, and time reversal symmetry breaking, which is the exchange field of the magnetic field. And as I emphasized, now it's the orbital field which is important, not the Zeeman. So why is it so important to go to, and that I hopefully will allow us to go to lower field, as I'm suggesting right now. So why it's so important to go to a magnetic field? So this is a summary of 3 different materials, 3 different experiments. You see in this is indium antimonide wire. The critical field, when we start to see Majorana's, is 100 millitesla. This is the indium arsenide. It's rather large, 700 millitesla. Tesla in the europium salt, in the aluminum, full covered. It's 70 millitesla, so it's really lower. And and what we will do today is to discuss the carbon nanotube. And my claim is that we can even go and push it a bit further lower to low to 50 millitesla. This is our predictions. Now, I just want to tell you that actually all these materials were mentioned in this paper. So the indium antimonide, the indium arsenide, the G factor was 50 for the indium antimonide. This is why you need only very low magnetic field. You use the Zeeman field in order to produce this effect. And indium arsenide has a smaller G factor. Therefore, you need this 700 millitesla. This is a new, the full shell story is a new thing, which is allow us to use mainly the orbital field. And also, actually, we were trying to do carbon nanotube already in this 2010 paper. But we did not succeed because the spin orbit coupling there was not in the right direction somehow. But we really try to do something carbon nanotube because this is the main thing. This is truly a one-dimensional object. So, you know, it's hollow. You can put flux through it. So this, what we thought will be very relevant to this type of experiment. So why it's so important to go to low magnetic field, why we really want it. And this is an experiment, again, came from Charlie Marcus group. So this is, this full shell wire is connected to transmon, and they measure some qubit oscillations. And what you see here, that in the first lobe, when the magnetic field is small, T1, the relaxation times are 2.5 microsecond. And as we go to the second lobe in the experiment, when we go to the second lobe, suddenly there is a huge reduction by factor of 5 or so of the relaxation time. So what is the origin? Why we have such large relaxation time? The answer is that we really don't know what is the origin, but we speculate that the authors of this paper speculate that somewhat shorter than in the zero slopes, which we speculate could be attributed to dissipation from subgap state present in the first lobe. So this is a usual situation. Yeah, I cancel that call. This is the usual situation when we have, always when we put magnetic field time reversal breakers, we produce impurity state or subgap states. This is kind of a general rule that we meet in many different circumstances since the origin. One second, let me answer that, otherwise they will continue to call. אני באמצע ההרצאה, כן. אז לא להתקשר בבקשה. שלום. So coming back to the talk, sorry, I'm sorry for that disturbance. So this is known from the original theory of Abrikosov when they include the theory that include magnetic impurities in superconductors. Magnetic impurities always introduce some subgap state. This is sometimes called gapless superconductivity. So we really want to create topology at small magnetic field, and it's truly one-dimensional system. And this is the discussion today, a step toward in that direction. So why carbon nanotubes? I'm repeating things which I already said. They are extremely clean. They are truly 1D. It's unlike the indium arsenide, which is full when there are states inside the the wire. Here we have only the shell around it. So we really, it's cleaner in that, it's supposed to be cleaner in that sense. It has strong curvature, induced spin-orbit coupling. We can put magnetic flux through the sample, that's clear. And this is our main conclusion of that talk. I will explain in detail how we get there, and I'm sure that it can be improved in a different way. This is kind of our initial estimate for the carbon nanotube. So, and this is a lower, our lower bound for the gap. I hope it will be better. We cannot, you know, we cannot predict everything, but for 50 millitesla, we predict that we will have a gap, a topological superconductor with a gap which is larger than 250 millikelvin. And the key point is that we put the carbon nanotube in proximity to niobium diselenide material. This is one of these new transition metal dechalcogenide materials, which has a very strong triplet component. So we make use of this triplet component that has a 3 Kelvin gap. Now the main idea that we'll do that we use the flux through the carbon nanotube in order to create half metallic state, only with one mode. I will explain that in details. I will explain that in details. And as I emphasize, Zeeman is present. Of course, we cannot get rid of Zeeman, but it's not necessary. This is not the main effect in this story. It's the orbital effect. So now I'm going to explain how this really works. I'm trying to do it slowly and explain really how it works, how we get this half metal, and how we tune the system to the right place. So what we need is a metallic carbon nanotube. This is the 3N3M. These are usually gapless carbon nanotubes. So as a prototype, I will discuss zigzag, but any metallic carbon nanotube, which is not the armchair, should work. Should work. So we know that when we cut when we have the carbon nanotube, so we look on the spectrum of the graphene, and we just have to, in the zigzag case, we have to draw diagonal lines that describe the quantization of the momentum along the circumference of the carbon nanotube. This is what we get if we do that. So the fact that it's gapless is because these lines in the 3NCM, these lines will cross the zero will cross the zero will cross the Dirac cones at k prime and at k. So this is why we will get a gapless spectrum. So this is what happened in the zigzag. Okay, 3 and 0. This is what happened in the zigzag when we have this point. We have a gapless. So now let's go slowly and see what are the physical effects, how the curvature and spin orbit coupling and magnetic flux change this picture. So curvature, what it does is, due to the curvature, these lines are pushed a bit inward. It has to be shown. You have to do some calculation in the theory to show that. But the way we could think about it is that the lines are here, and the lines are here. So that now we don't cross the Dirac cone at the 0 points, but we cross it at a different point, and therefore a gap is open in the system. So this is due to the curvature. So now I'm going to just concentrate on the main thing. This is just as similar to the previous picture, but I just enlarge that part, which I want to concentrate on that. So the curvature open a small gap in a zigzag or any non-armchair situation. Now, when we put flux through the system, so again, what flux do, it's push these two lines downwards. So due to time reversal symmetry, the distance of this line from the Dirac point and that line from the Dirac point must be equal. They both have the same mass. Now, when I put flux through the system, it changed the quantization condition on the momentum around the circumference and push these two lines downwards or upwards. That depends on the direction of the magnetic flux. So one of the modes go away from the Dirac point, so it has a larger gap, and the other one goes towards the Dirac point, so it has a smaller gap. So in this way, now these states are still degenerate. So it's still not half metal. We have, instead of having both K and K prime, we'll have in this case only K, but it still will have spin up and spin down. So now the question is what happened when we add spin-orbit coupling. So spin-orbit coupling works very similar to the magnetic flux, but spin up will acquire positive spin-orbit flux, and spin down will acquire negative spin-orbit flux. So it split the two lines, the up and down, in this fashion. So if we look down here, you see that the up spin will have a large gap, while the down spin will have zero gap. It will, if we tune the parameter properly, we push it to the Dirac point. So in this way, only the flux, no Zeeman field, we tune the system to a half metallic situation. We have only spin up in the system. Now, when we say up and down, I want to emphasize that the up and down meaning the spin along the carbon nanotube. So up meaning is in the Z direction, which is along the nanotube. Up meaning, that's depend on the coordinate, but up meaning in one direction of the nanotube, and down meaning in the opposite direction of the nanotube. And the way to remember that and to think about it is that these K modes are in fact describe this quantization around the circumference. It's in fact describe have some angular momentum around the circumference. So this spin orbit coupling is like L dot S, where L is the orbital angular momentum due to the motion around the circumference of the nanotube. Okay. So this is a summary of what I discussed so far in a three-dimensional fashion. So we have these 6 Dirac cones with equivalent K and K prime. The flux, the curvature push these lines a bit inwards. The flux push them down. The spin orbit coupling split them. And in this way, we can tune the gap in the system so that we have eventually only one mode with small gap. The other has larger gap. Now, by the way, the effect of the Zeeman field, if you want to include it, will cause this one cone to split to two, to spin up and spin down in that fashion. So it doesn't move the quantization condition, but it changed the Dirac cone in this fashion. So all these figures are very, for me, they were very helpful to understand intuitively what each component do in the problem. So in this way, we have half metal, but it has a finite momentum, this half metal. It has finite angular momentum around the circumference. So even if I manage to find a superconductor which will couple somehow this equal spin state, this half metal, by additional spin orbit coupling, for example, then I will still need also to give the momentum, the proper momentum. But actually, when you think about it, when I put the carbon nanotube on the substrate, the angular momentum is not conserved anymore. The upper side of the carbon nanotube is different from the lower side, so the angular momentum is not conserved anymore. So these are the two ingredients that we need. First, to create half metal, and the fact that K pair is not conserved. And I still need to somehow couple the two spin, which are both the two electrons with equal spins. And I will show you how to do that right now. So I don't know if are there any questions so far, because this is kind of important to understand how it is working.
So there is one question.
Yes.
From Sanoli, who says, despite curvature effects, spin orbit coupling in carbon nanotubes is still much smaller with respect to 3-5 nanotubes. How much this is a limiting factor to have Majoranas?
Okay, I will discuss the experimental parameters later on. So we think it's possible to do that. We put the right number. And you can also, in addition, you can have a gate which tune the whole thing to the Fermi level to the right position. So your Fermi level doesn't have to be exactly at the Fermi point. But the important thing is to create difference between the different states, so that I can tune the chemical potential such that I occupied only that curve. But I will discuss that in detail. That was the only question. Okay, good. So so let's assume that, and actually there are different experiments only on carbon nanotube that do show that you get this half metallic situation.
Yuval, since we stopped here, let me ask you one more question. What is the role of the radius of this?
I will discuss. So you want it small, so the spin orbit coupling will be large, but you don't want it too small because then you need large magnetic field. So you have to find an optimal value. Okay. Okay. The computer is stuck for a reason that I don't know why. Don't know what to do.
Perhaps you have to stop sharing.
Yeah,
and then...
maybe
no, the mouse doesn't work.
Maybe stop sharing and open it again.
Perhaps for the rest of you is the moment to ask questions through the chat so that I can read them at the end.
The computer is frozen. I don't know what to do.
So
I don't know what happened. Maybe this was the reason why they called me earlier.
Oh.
It's back.
It's back. Ah, well,
good.
Fantastic.
Good.
Good. So, well, okay. So, so what are these niobium diselenide? So the main important thing about this niobium diselenide material is that they are the so-called Ising superconductors. I'm going to explain to you what are Ising superconductors. So this is the behavior, the spectra of these systems. So what niobium diselenide is a two-dimensional exfoliated material, similar to graphene, that you can separate it to layers, and you have a layer of niobium and a layer of selenide above and below. And the band structure of and there is a huge spin orbit coupling. What we see is a band structure very similar to graphene. You have something at the gamma point, something near the general structure, something near the K prime point and the K. And the important thing is that there is a huge spin orbit coupling here, which separates spin up and spin down. So you can appreciate that in this figure, in figure D here, that the scale here is electron volt. So if I look at the difference in the energy at this point between spin up and spin down, it's of the order of 0.1 electron volt. These are numbers that we don't know, we're not used to indium arsenide or indium antimonide. These are huge numbers. Now, so let me concentrate on that part. So yeah, so and so the important thing is that the spin-orbit coupling is such that the spins point out of the plane. And what hold them are huge forces with energy gap of the order of 0.1 electron volt. So these materials are very special in that sense. First of all, superconductivity survive even in monolayer. So what we see here is TC as a function of the number of layers. So for many layers, it's about 7 Kelvin, and for one layer, it's become 2.7 Kelvin. Depends exactly how you define. So even for one layer, you have superconductivity, and they survive because of these huge out-of-plane spin-orbit coupling. They survive up to 32 Tesla. These are numbers that we don't really know. Okay, so this is the result for these materials. So there is a huge spin-orbit coupling, and in principle, even monolayer, we can have monolayer, and this is, by the way, allow us to put an additional gate to change the Fermi level in the system if we have this device of EMD and carbon nanotube. So concentrated in that, these are the spin up and spin down. And now what I want to show that with this Ising material, we will be able to have this coupling of parallel spins in the carbon nanotube. So the important thing is that, you know, these two have two very different energies. So imagine that we have superconductivity delta 1, which is C dagger K prime down, with CK up, and there could be a different, and because they are a different position and so on, it's very reasonable that they will have delta 2, which is not equal to delta 1, because they are not at the same point. And now, if I write it in the way that we are more familiar with, I define delta 1 to be delta T plus delta S, and delta 2 to be equal to delta T minus delta S, then it's acquired this form. So only when delta 1 is equal to minus delta 2, namely when the delta triplet is 0, we'll have only the singlet component. Usually, and this is what people believe, that in this material, we have a large triplet component. By the way, this still does not break time reversal symmetry. It's a perfect time reversal superconductor, which has a large triplet component. Now comes the nice thing. Remember that here the spins are up and down, and in the carbon nanotube, what we say were two up spin in the same direction. So if I try to write this spin in the direction perpendicular to the TMD in terms of electron spins parallel, which are inside the carbon nanotube, and I plug it in the triplet component, if I plug that in the singlet component, it will not change. This will be just a rotation of the basis. But if I plug it here, I will get terms which are proportional to the same spin in different K and K prime. And so in this way, I will get a triplet component. So here we more or less was the main idea. Here I explain the physics. So there is a carbon nanotube, which we can tune to be half metallic. We put it on top of an Ising superconductor, so that can couple both identical directions of the spin in the nanotube, and we take advantage of the fact that K is not conserved, and we can, because I do not cover the whole carbon nanotube. So now, right now, we still have, so now I'm going to describe, this was, I hope I explained slowly the main idea. Right now, I'm going to rush a bit on, because these are just numerical simulations of this idea. So this is the model that a continuum model that we write. There will be a term which describes the coupling between the valleys, a term which will describe the spin, a term which has the sublattice, and nu is the valley degree of freedom, And these are the estimates for the different parameters in the system. There are two types of spin-orbit coupling for nearest neighbor, next nearest neighbor, but they are of the same order, 1 milli-electron volt divided by the radius of the nanotube in nanometer. And this is the scale in which we shift these Dirac cones from the Dirac point as a function of the magnetic field. And the Zeeman field, you see for 1 nanometer, it will be much smaller than, much larger than VZ. So this is where the Zeeman term is gone. And in the simulation, we include them, but it's not really important. The important thing is the orbital field. So this is, I'm rushing here with, this is just to show that our continuum model reproduced very nicely the tight binding model and all the effect of the coupling between the Ks, the spin orbit coupling, the magnetic flux, and the second type of spin orbit coupling, the next nearest neighbors. So if we start from a metallic carbon nanotube, so we do the simulation of 12.0, this is really small, and this allows us really to do full tight binding calculation of the system and to compare to the continuum model. So this is a standard. We didn't include here the curvature effect, but that could be included. Then when we include coupling between the two cones, it's split them. The K and K prime, it split them. When we add this alpha term, we already open a gap in the Dirac cone. And we split. We get instead of 4 when K prime spin up, spin down. Now we have already only, it's split to 2 doubly degenerate bands. And when we add the magnetic flux, we get this behavior. And the last thing that we have to add is this alpha prime, which was important in order to get this state, which is half metallic, and it sits both on K and K prime. Yes, this was including this coupling between K and K prime. So this is a simulation that shows, so theta is, when theta is 0, that meaning you sit only on K. If theta is pi, then that means that you sit only on K prime. If nu, it's equal. And any value between them, meaning that you have some component in K and K prime. This is what we need because the TMD give us coupling between the two between the two spins. So again, that's the device that we have in mind, and we think it will work. And now what I would like, and a full simulation, which we did only for something which is not realistic in the laboratory, but we did perform a full simulation of the system for 12.0. Here we need, because it's so small, we need to put a huge magnetic field in order to get magnetic flux. But in reality, if it will be larger, that was just to allow us to do the full simulation. You know, each atom was a site in our tight binding model. And then we could compare to the continuum model and estimate the two results from the continuum model. So that's just showing that as we change the gate potential, we can tune the system to the half metallic situation. And this is the topological phase diagram when we include the coupling to the TMD, assuming that we have a triplet component in the TMD, which is similar to the singlet component in this 0.3 milli-electron volt. So here we need, again, because it's very small, we need very large magnetic field, but you see that we can tune the system to a topological phase with a gap, which is not negligible compared to the triplet gap, which is induced from the TMD. So this is a real space calculation of the tight binding, just to show that we get indeed these Majorana modes in this simulation at the end of the wire. And we see all what we all saw in many simulations and Majorana system, that as you change the chemical potential, you see this one topological region, and then because here we have two, as you see here, we have two very close topological states. So in fact, what we see here is one topological state and a transition, which is non-topological, and in this case to another topological state. So it seems to work, at least in the theory. Now we can think, what I would like to say is that we studied niobium diselenide, but in fact the same theory will work to different material, to tantalum disulfide, to tungsten ditelluride, to molybdenum disulfide, and other. Also ultra thin layer of lead has strong spin orbit coupling. They can work as well. And you can think about more exotic situation in which you put a carbon nanotube on twisted bilayer graphene that has superconductivity by itself. And it would also supposed to have a strong triplet term because of the repulsion between the system. Now that I think this is wrong. These numbers are wrong, but this is to compare results. So this is what we get for R equal to 2.5. I'm sorry, this is a mistake, but we got this numerically. We got this gap, which is 0.1 milli-electron volt. And then if we use this scaling behavior that the spin orbit coupling is, 4 times smaller when I increase R by a factor of 4, and the here it's reasonable number, and this shift of the flux is proportional to R, then the gap will be 4 times smaller because the spin orbit coupling is 4 times smaller, but this is kind of a boundary. The magnetic field will be, now R is 4 times larger, so the magnetic field that we need in order to have the same phi will be 4 times smaller. This should bring us to 50 millitesla. So these numbers are estimates. They should not be taken, they should be taken with a grain of salt. But we believe that this is a direction to use the orbital effect in order to reduce the spin orbit, in order to reduce the magnetic field which is needed to create this system. So yes, time is over. Yeah. 1 minute.
Well, yeah, you should finish already because we want to have few questions. Okay, so I will skip. In fact, as I said, in fact, the carbon nanotube also have interaction in the carbon nanotube. So you can, I didn't know if I will have time for that. So I'm prepared that just in case I'm finished earlier. So there is a way to use the interaction in order to create also interesting, utilize the interaction in order to create interesting time reversal invariant topological superconductor. So I don't have time to explain that, but the carbon nanotube have strong repulsion inside the nanotube. And then even without any magnetic flux, you can create an interesting topological state, topological time reversal topological superconductor, which have pairs of time reversal Majorana modes. I don't have time to explain that. There is a review of that if you would like to, another review from 2019 that you can read about it. Let me skip that part, let's explain that. So this is my summary. Carbon nanotube and transition metal with small flux. We need a TMD triplet component. Majorana 0 modes will appear at low field. And this time reversal invariant topological superconductor can be established due to interaction in this system. So I know that there are many experimentalists in the audience. I think this is an extremely interesting material to study. I didn't mention at all the possibility, to rotate to the orientation of the carbon nanotube with respect to the TMD. This is also interesting. You can think about some dependence on the angles. So I didn't discuss that at all. So I think this is a really interesting system, and I hope that more research will follow. So thank you. Thank you very much, Yuval, for this wonderful talk. So let's go to a couple of questions from Christoph Strang. how sensitive is the topological gap to the relative orientation between the carbon nanotube and the niobium diselenide crystal lattice?
Okay, you just said we did not study that carefully. This is, I think it's an interesting question. I mentioned it at the end, that the angle, it has to be a nanotube with small gap, so it has to be this 3N 3M carbon nanotube, not an armchair. For an armchair, it doesn't work all this story because the flux, they don't respond to the flux in the same way. But we didn't study the orientation yet. The way we treat this TMD is just to put the delta in a platform. This will be very interesting to study. In our simulation, we just put a delta parameter, a pairing parameter, which we assume is induced by the TMD. I think it will be very interesting to study the orientation.
Very well. And Nicola Paradiso says, how crucial is it to have monolayer niobium diselenide?
Not very crucial.
Okay.
Not very crucial. I thought that will enable also to gauge the whole sample, and so it may be easier, but we think it's, as long as there is an induced superconductivity from the niobium diselenide to the carbon nanotube. And that we know that happened. There were some experiments that actually explored that option.
Okay, and I have one question. Yuval, do you think you could have also here in this system the problem of the quasi-Majoranas?
Yeah, that's of course, you mean quasi-Majorana, the carbon a dot at the end and all that question. Well, I think the physics will be, always we will have that problem, but in principle, we can create these Majoranas in the middle by changing the condition along the nanotube. That can, if you stretch that, or you can do other things. But in principle, I think all these samples suffer from the same problem.
Variations of chemical potential.
So there is no magic. It's, yeah.
Maybe a sort of related question is, maybe you mentioned, did you consider the role of S-wave components and the formation of Andreev bound states in such clean system?
So what, in the simulation, what we did, the simulation was simply to have finite size system.
Right, but there do you have S-wave components also that may appear?
Yeah, we include S-wave components.
Okay, okay. Thank you.
Some, not all of them, but in some of the simulation we include them. It's it's actually in some cases it helps to remove. It's even better when you have the S-wave component because it remove other states which otherwise are inside the gap.
But you don't have subgap states like quantum dot like subgap states from these S-wave components in the nanotube.
So the way we studied that was to have a very sharp. All these questions are of course relevant, but we just, we didn't study them. There are no experimental results. By the way, you can imagine STM experiment in this system, which simply, tunnels through the whole sample. You come with an STM and you measure the carbon nanotube along its way. This is an open system. It's it's challenging, of course, but we so many experiments about STM on carbon nanotubes. So that is another. But the questions about the quantum, the dots are relevant, they're important, and not try to hide. We just didn't study them in detail. So hope we can study them together. It's an interesting subject.
Very well. So thank you very much. There are no more questions, so please we go to the next speaker because we are a bit tight with time. So the next speaker is Samuel Díaz Escribano from the Autonomous University of Madrid in Spain. And he's going to talk about Majorana bound states in semiconductor ferromagnetic insulator superconductor nanowire heterostructures.
Hello, everybody. Thanks, Elsa, and thank you, the organizers, for giving me the opportunity to share my work. I'm Samuel Díaz Escribano, and I'm going to show you that it is possible to create Majorana bound states in usual semiconductor superconductor nanowire heterostructures without applying any magnetic field. And this can be done if the heterostructure is also proximatized with a ferromagnetic insulator. So this work is in collaboration with my PhD advisors, Alfredo Levillati and Elsa Prada, and also in collaboration with Yuval Oreg. And I would like to also thank the discussion with Sailu Vaitekanas and Charlie Marcus. So as you may know, Majorana bound states are topological subcap modes that emerge at the ends of the superconductor semiconductor nanowires under certain conditions. So these Majorana bound states are usually described using the Lutinoren Hamiltonian, which includes a kinetic energy term, an electrochemical potential, a spin-orbit interaction, which is present in these semiconductor nanowires, and a superconducting pairing amplitude, which is induced by the superconductor in the nanowire. To create this Majorana bound state, it is also necessary a Zeeman field, which is induced by applying a magnetic field along the wire's direction. So as you may know, because of the exotic properties of these Majorana bound states, they are known to be useful for topological quantum computation, but due to the magnetic field, this magnetic field weakens the superconductivity and therefore the topological protection of these states, and also complicates the scaling of a hypothetical quantum computer because all the wires need to be aligned with the magnetic field. So the question is if it is possible to create Majorana bound states without applying any magnetic field. The answer is of course yes, and this is something that sorry, during the last year the groups of Copenhagen have been working on. They have shown that it is possible to intrinsically incorporate the effects of an exchange field in this heterostructure if this heterostructure is also proximatized with a magnetic insulator layer, in this case, europium sulfide. So in this work, they show here in this picture the conductance versus the backgate voltage through this nanowire, and they show that there is a zero bias peak which is compatible with the existence of Majorana bound states. Strikingly, they also show that there are other geometries which show no induced magnetization. So from a theoretical point of view, we want to understand and to study whether this zero bias peak could be or not Majorana bound states, and why these two devices do not show zero bias peak. So in general, we want to understand how the magnetization is induced in these heterostructures. To do so, we use two different models, one that we call realistic model, that is useful to understand the magnetization in this system, and another one that we call effective model, which is useful to study the phase diagram of these heterostructures. We applied these two models to these two devices. This device, we call it overlapping device because the aluminum and the europium sulfide are in contact in one facet. This device is the one that shows zero bias peak in the experiments. And this other device that we call non-overlapping device because these two materials are not in contact, which doesn't show zero bias peak in the experiment. So let's start with the realistic model. Within this model, we include in the Hamiltonian not only the indium arsenide nanowire, but also the europium sulfide and the aluminum layers. In this Hamiltonian, we include the kinetic energy term with the effective masses of these three materials, the Fermi levels of these three materials, where the conduction advantages of these three materials, the exchange field in the europium sulfide, the superconducting pairing amplitude in the aluminum, and the spin-orbit interaction in the indium arsenide nanowire. This spin-orbit coupling is given by this equation in the nanowire. And if you are interested in this equation, I have a pre-recorded talk in the spin-orbit physics mini-symposium where I explain it in detail. So we also include the electrostatic potential, which we computed solving the Schrödinger-Poisson equation self-consistently in the Thomas Fermi approximation. To this end, we include the electrostatic environment, which means that we include the left and right subgates that are present in the experiment, and also the backgate potential, and the band bending between the aluminum and the indium arsenide nanowire. And in addition to this, we also include the charge accumulation layer that is typically present at the phase edge of the semiconductor nanowires. And the remaining dielectrics are also included with their corresponding dielectric permittivities. So we discretize this continuum model, what leads to a tie-binding Hamiltonian that we can solve numerically, and we can obtain the energy spectrum by diagonalizing it. We only perform the discretization in the section of the wire, and we assume that in the other direction, in the Z direction here, the nanowire is translational invariant, and therefore KZ is a good quantum number. So we can obtain the energy spectrum from this Hamiltonian for this heterostructure. And this is what we do here for the overlapping device for 3 different cases. When the spin orbit coupling and the exchange field are turned off, and then we study what happens when we switch on the exchange field first and then the spin orbit coupling. So let's focus first on this plot. This is the case where the spin orbit coupling and the exchange field are turned off. So in these 2 plots, we plot the same energy spectrum, which is the energy versus KZ, the momentum along the wire direction. With colors, we show the weight of the wave function in a certain region, in this case in the superconductor, and in the top panel in the wire. So here black means that the wave function is completely localized in the wire in this case, or here in the superconductor. On the right, we show the density of states corresponding to the plots on the left. So what we see here is that for the case where there is no spin orbit coupling nor exchange field, the induced gap in the semiconductor is smaller than the parent gap and is of the order of 0.2 milli-electron volts for these voltage, for these gate voltages. This is the distance between the coherent peaks. If we now turn on the exchange field, what we see in the semiconductor is that the gap is closed. And this is because the induced Zeeman field or exchange field is larger than the induced superconductivity. On the other hand, we see that in the superconductor, the gap remains almost open, but the coherent peak is doubled. And that means that there is a small exchange field also induced in the superconductor. And this is something that previous experiment showed for aluminum European sulfide heterostructures. Finally, if we also turn on the spin orbit coupling, what we see is that in the wire, the gap reopens again. A gap is reopened again. And this is a signature of a topological phase transition. We believe that these states here that are closed and now reopen again, are Majorana zero modes. Of course, to make sure of this assumption, one will need to compute the topological invariant, and this is something that we are currently doing. Okay, now we understand how it works, the overlapping device. Let's move on to the non-overlapping device. We compute exactly the same simulations as before. So for the case where there is no spin orbit coupling or exchange field, we see more or less the same features. But when we turn on the exchange field, what we see is that more or less nothing changes. So that means that for this non-overlapping device, the induced exchange field seems not to be large enough to close the gap. What in turn means that there is no topological phase transition or no topological phase in the non-overlapping device, at least for this gate voltage. To make sure of this statement, one would need to compute the topological phase diagram for this device, but this is not affordable for the realistic model since one has to include the aluminum and the European sulfide in the simulations, what makes it a very expensive computational model. To overcome this problem and to compute the phase diagram, what we use is what we call the effective model. Within this model, we integrate out somehow the aluminum and the European sulfide layer, and we directly include the proximity effects inside the nanowire. So we say that there is a region close to the aluminum interface, here in black, where there is a superconducting pairing amplitude smaller than the parent gap, as well as a small exchange field. This exchange field is the one that is induced in the superconductor by the europium sulfide. On the other hand, in the region close to the europium sulfide, here in red, we assume that there is a large exchange field, but in a very narrow region. And this is because the europium sulfide at the end is an insulator. So now we can use exactly the same Hamiltonian as before, but now this Hamiltonian only applies to the nanowire inside. So we can diagonalize now this Hamiltonian as well, and we can compute the topological invariant. And this is what we do here. So this is the phase diagram for the overlapping device versus the backgate voltage here, and the exchange field in the europium sulfide interface. So we are not saying that this parameter is tunable, but it's just that it is not very clear from experiment, which is its precise value. So here white means that the lowest energy mode is topologically trivial. And in color, we saw the lowest energy modes that are non-topologically trivial. With colors in the top panel, we saw the induced magnetization for the lowest energy mode. And in the bottom panel, we saw the mini gap for the lowest energy mode. This mini gap is the lowest energy gap in the system for the lowest energy mode. So what we see here is that there are different topological regions. Some of them are narrower or larger, and with an induced exchange field smaller than 0.4 millielectron volts, and with an induced mini gap smaller than 0.6 times the induced superconductivity, the parent gap. We can compute the same simulations as before, but versus the right side gate here. We see also different topological regions. And as one increases the right side gate, the mini gap decreases. But the induced Zeeman field remains almost constant. To gain more insight into these features, we plot here the wave function of these states, and on the right, the total charge density at these points. So what we see is that as one increases the right side gate, the wave function is pushed towards the right side gate, and in turn pushed towards the europium sulfide layer here on the right. That means that the wave function goes far away from the superconductor, and therefore the induced superconductivity is smaller, what in turn means that the mini gap should decrease as well. But the exchange field should remain constant, as I showed you before. If one computes now the same topological phase diagram for the non-overlapping device, what we see is that there is no topological phase for negative right side gates. And this is because the wave function is mainly localized in these three cases in the aluminum indium arsenide interface, what means that there is no induced Zeeman field. But there is topological regions for positive right side gates. That is something that was not very explored in the experiments. And this is because the wave function is now spread all across the nanowire, and therefore it has both components, induced superconductivity and induced Zeeman field. So to conclude, I have shown you that these kind of heterostructures, indium arsenide aluminum europium sulfide heterostructures, can intrinsically incorporate the effect of a Zeeman field, which could be large enough to support Majorana bound states. However, and due to the interplay between the Majorana, the position of the wave function and the interfaces with the europium sulfide and the aluminum, only some specific geometries give rise to Majorana bound states. Fortunately, this can be controlled by tuning the gate potentials. And now what we want to understand and to study is how looks like the Majorana bound state wave function, and how the energies look like for finite size nanowires. And we would like to compare them with experimental data. So if you have any question, you can ask me now, or you can contact me via email. And that's all. Thank you for your attention.
Thank you very much, Samuel, for this beautiful talk. So please, do you have any questions?
I have a question, if I may ask.
Yes.
Okay.
So for the realistic model, something that I didn't get, how do you calculate the exchange field?
So, okay, in the realistic model, we include in the European sulfide, we only include in the European sulfide exchange field. So we use realistic parameters that we obtain from the literature. And this exchange field is the Zeeman splitting in the conduction bands, which is 100 millielectron volts.
I see.
It's something that is obtained from ab initio calculations and from experiments from the conduction band. And in the rest of the materials, there is no exchange field.
Okay, but it's not like a proximity, like you calculate the proximity effect of this exchange field, or you just put the exchange field, right, in the model?
Yes, I just put the exchange field in the European sulfide. So somehow this European sulfide is proximatizing the rest of the heterostructure with a Zeeman field.
So you put it in the European. It's not that you invent how it goes into the nanowire.
Yes.
The same way that you put a pairing in the aluminum.
Yes, exactly equal. Exactly the same.
In this realistic model, then
Elsa,
yes, I know there are questions. There are questions. Yes, I know. Okay, so now there are some questions in the chat. Eduardo Lee asks, can quasi-Majoranas be a problem in this type of system?
For sure. I mean, something that is not clear for us is whether these zero bias peaks are Majorana bound states or are quasi-Majoranas, because they could be both. So you have the same problems here than in usual semiconductor-superconductor heterostructures. You have a quantum dot and you have an inhomogeneous potential that could give rise to these quasi-Majoranas.
Very well. So Quinsen Wang asks, why is the W superconducting 30 nanometers larger than W exchange 1 nanometer in the simulation?
Yes, I didn't explain it with detail. What we do to obtain these parameters, so here the width of this proximity effect for the superconductor is 30 nanometers, and the width for this proximity effect with the European sulfide is 1 nanometer. So we compute these widths by computing the induced magnetization and superconductivity using both models, the realistic model and the effective model. And we choose these widths in such a way that this effective model reproduces roughly the same behavior as in the realistic model. So the ultimate reason why this width is larger for the superconductor than for the European sulfide is that the superconductor is a metal. So somehow it attracts the wave function inside the aluminum. And therefore, the weight of the wave function is larger close to the superconductor. And therefore, the induced superconductivity applies for a wider region. On the other hand, the European sulfide is an insulator, and therefore the wave function cannot be close or prefers to be outside this region, and therefore the proximatizing region is a very narrow region.
Very well. And the last question, Ruben Sebane asks, do you understand why the nanowire with 3 facets covered by aluminum does not exhibit a zero bias peak?
Yes, let me show you this. So these are the same simulations. Okay, these are the same simulations, but for the 3 facets nanowire. So in this case, this is the same figure that I showed you before. And we see that there is no zero bias peak for this case. This is without the spin orbit coupling. So the gap is not closed, even there is exchange field. And this is because the wave function prefers to be localized at this corner, because the band bending between the aluminum and the indium arsenide is larger than the band bending between the europium sulfide and the indium arsenide wire. So because the wave function is here, it does not feel the exchange field in the europium sulfide layer.
Okay, so we are going to leave this here and go to our next speaker. So our next speaker is Lena Wittermann from Technical University Braunschweig in Germany, and she's going to talk about probing Majorana bound states with an optical quantum dot. So I give you the floor.
Thank you. Can you see my screen?
Yes.
Yes, go ahead.
Okay. So thank you for the opportunity to present our work here, which I did with my colleagues Daniel Frombach and Christoph de Boele and my supervisor Patrick Recher. And we consider a Rush-Bar nanowire in a magnetic field, which is separated in 3 regions. In the blue region, it's in proximity to a superconductor, and in the topologically non-trivial phase, Majorana bound states emerge at the ends of this part of the wire. Then we have this red wire here, which is a whole reservoir and coupled to a normal lead. And in between, there's a quantum dot. And in the PN junction of the quantum dot, electrons and holes can recombine to photons, which are emitted in wire direction. And we want to investigate the signatures of the Majoranas. So such a wire system was first proposed here. And it was experimentally shown that for increasing the Zeeman energy, one can find a zero bias peak emerging, which is a signature of Majorana bound states. In such a wire, the 2 Majorana bound states are mostly localized at both ends of the wire, but the wave function decays exponentially into the wire. So for a finite length of this wire, the 2 Majoranas have a finite overlap, and you can find also the contribution of the right Majorana bound state close to the boundary here. You can also define Majorana spin angle with the electronic components of the wave function. And for increasing the Zeeman field, the angle of the right Majorana tilts here at this boundary. These are all electronic probings, and we want to investigate the photon emission. And it was also proposed and also in an experiment shown that you can get photon emission from superconducting reservoirs. Also, the coupling of Majorana bound states to electromagnetic fields is not a new idea, as we also saw yesterday. So you can couple them to a microwave cavity or use a Josephson junction where you get this Josephson radiation. So let's move on with our effective model. We have electrons in the conduction band of the quantum dot, which are coherently coupled to the Majoranas, gamma 1 and gamma 2, which can have a finite overlap psi. And in the valence band of the quantum dot, we have holes, and the electrons and holes can recombine to photons with this V-rec here. So let's look at first at this part where the electrons are coherently coupled to the Majoranas. So we have here the quantum dot Hamiltonian, where the quantum dot energy is epsilon, and the 2 single spin levels of the quantum dot are split by this Zeeman energy delta Z here. This is the term for the double occupancy of the quantum dot, but we assume a very large charging energy so that we are in the single occupied regime. The Majoranas are described by this Hamiltonian here, where we have the splitting psi, and gamma 1 and gamma 2 are the Majorana operators. The tunneling is defined like this, where we have spin-dependent tunneling amplitudes to gamma 1 and gamma 2. If we now use the non-local fermion basis, like this here with the non-local fermion operator C, we find that this Hamiltonian here, where we have the occupation number of the non-local fermion, and we have this tunneling term here. We use the occupation number basis, meaning the number of dot electrons and the number of the non-local fermion. And you can see in the tunneling Hamiltonian here that you get 2 terms. You get one non-local pairing term. This is a term which can create a pair of electrons where one goes into the dot and one is the non-local fermion. And you get terms of tunnel processes between the dot and the non-local fermion. So therefore, states of even and odd parity are decoupled. And what you can also see here is that the non-local pairing and the tunneling processes are different with this non-local coupling here. So for finite coupling to the second Majorana, these two tunneling amplitudes get different. So let's look at the spectrum of this part. So here we look at the dot coupled to only one Majorana, and note that we always assume that the coupling to up spins is smaller than to down spins, which would be the case for a nanowire in a Zeeman field. So here's the spectrum. And here you can see two resonances in the spectrum, and you see that even and odd states are degenerate. So here is the coupling for up spins, and here's the coupling for down spins. And as I told you, we see that this anti-crossing is much larger due to a larger coupling to down spins. If we now introduce a finite splitting between the Majoranas, we can see now 4 avoided crossings in the spectrum, and even and odd states are split by Xi. Here, the dashed line are odd states and the solid lines are the even states. Again, the avoided crossings for down spins are larger. And now we introduce a finite non-local coupling to the second Majorana. And what we can see now is that the avoided crossings get different, here for upspins and here for downspins, which I told you is because of the fact that now even and odd states couple differently. So let's move on with our setup. For the recombination, we have our electrons in the conduction band of our quantum dot, which are our eigenstates in the even and odd parity sector, which I presented you. Then we have also holes in the valence band of the quantum dot given by this Hamiltonian here, where the holes are also split by the Zeeman energy and can be doubly occupied with charging UH. Then we also have the photon bath, where we have photons with momentum K and polarization P, where the polarization can be left or right circular polarized. The recombination is determined by this here, where in this scheme you can see that up electrons always recombine with down holes to left polarized photons, and vice versa recombine to right polarized photons, because here the angular momentum is conserved. For the transition rates, we use Fermi's golden rule. And for the dynamics of the system, we can use a Pauli-Master equation, which describes the occupation probabilities of our eigenstates in time. So we have rates which go into our state psi, and we have rates that go out of our state psi, and therefore we lose occupation. We can find a steady state then with a derivative of our rho, which is equal 0, and then we have the steady state. In this master equation, we include the optical recombination rates, which we calculated with Fermi's golden rule. And in the presence of a hole reservoir, we also introduce a hole refilling rate, gamma H. If we look at our uncoupled states, again, this was the quantum dot electron, and this is the non-local fermion. Then an up spin can recombine with a hole to left polarized photon, ending up in a state like this. And here we change the parity of the system. The same holds also for down spins. If we recombine, we get a right circular polarized photon and change the parity of the system. In the whole subsystem, if we start in a doubly occupied hole state, one recombination will give us a singly occupied hole state, and we can refill this with this hole refilling rate, gamma H. So the total emission intensity integrated over all photon energies is then given by the rates which going out of our state psi times the steady state solution of the state psi. And with this, I would like to come to our results. At first, I show you the case of separated Majoranas, where we only couple to one Majorana. To remember you, this was the spectrum here, where even and odd states were degenerate, and we had 2 resonances in the spectrum. In our intensity, we can see 2 peaks emerging at these resonances, exactly again at plus and minus delta Z. And you see that both have the same maximum, and therefore we can think about an emission cycle. So if we start in an even state with an electron, then we can recombine, send out a photon. Due to tunneling, we come back to a state with an electron and can recombine again. And therefore, exactly at these positions, we have the maximal emission intensity. If we look at the dominant processes in the system, we can have an analytical expression for our intensity, and we see that the widths of the peaks are proportional to the tunnel couplings to the first Majorana. Now we introduce a finite splitting between the Majoranas, and this was the spectrum for this case, where we now have 4 anti-crossings. And what we can see in the intensity is that we still have peaks centered around plus and minus delta Z, but now the emission intensity is much smaller, and also for left photons, it's smaller than for right photons. If we now look exactly at this anti-crossing of odd states, we can find an emission cycle like this. If we start here in an even state, we recombine once, then the tunneling is very strong to the other odd state, and we can emit another photon and are now in an even state. But because this coupling here is weak, we find a suppressed emission. And the same holds also at this position here, where even states have an anti-crossing in the spectrum. So the best emission intensity is given exactly as at plus and minus delta Z. And what we can see in our analytics is that a finite splitting will decrease the height of our peaks and increase the width of our peaks. And this third case I want to show you is if we introduce a finite non-local tunneling to the second Majorana. Here was the spectrum where we saw that now the crossings between even and odd states are different. And for this, we can find from, we see now in the intensity that the peaks are shifted away from this plus and minus delta Z. So for the left polarized photons, we see a shift to the left side. For right, we see a shift to the right. And from our analytics, we can see that the shift is given by this here. So for finite splitting and a finite coupling to the second Majorana, we find a shift of the intensity peaks. And this is a signature of the non-locality. As I told you in the beginning, we investigated this nanowire model, and therefore we take a numerical calculation where we discretize the model on a lattice with n sides. Therefore, we get the Majorana wave function at the left end of the wire where the QD is coupled to, and we take the electronic components so that the tunneling amplitudes are then proportional to the electronic components at side n equal 1. From this, we extract the splitting and also the tunneling amplitudes as a function of delta Z. And what we can see now is that if we take a long wire, here you can see the down component of the coupling to the first Majorana and the up component. So the down component is much larger, and for small magnetic fields, you see that the splitting and also the coupling to the second Majorana are almost 0. So this is the case of the separated Majoranas, and for this we can find in the emission intensity again 2 peaks of maximal emission, and with the width of the peak we saw that this is proportional to the tunneling amplitudes, and for the Majorana spin angle we can parameterize it with just one angle since it's in one plane, and therefore you can find the Majorana spin angle, which is in this case 164 degrees. If we now go to a short wire, you see that here in red and green, the coupling to the second Majorana is much larger for smaller Zeeman energies, and the dashed line here, the splitting, also oscillates and is also larger. In this case, so for this given delta Z here, we find the emission intensity where all the couplings are finite, and you see again that the 2 emission intensities are different, have a different height, and we see a slightly shift to the left of the right peak and a shift to the right of the left peak, which is again a signature of the non-locality. And with this, I would like to conclude. I showed you our effective model where we coherently coupled electrons to Majorana bound states, and electrons and holes on a quantum dot can recombine to photons. The dynamics of the system are described with a master equation, which is then just a simple Pauli master equation. And in the polarization resolved emission, we could measure the Majorana spin angle for separated Majoranas, and we saw the non-local signature, which was the shift of the emission peaks here. And we think this is an alternative to transport measurements where we have direct access to the spin. And with this, I would like to thank you for your attention.
Thank you very much, Lena, for this wonderful talk. So there are some questions in the chat. Sunhoon Park asks, why do holes in quantum dot not couple to Majoranas?
Yes, so for the master equation, we assume that the energy between the holes and the electrons is much, much larger than all the other energies. So we say that the holes are energetically separated from these Majoranas, and therefore we can neglect all the coherent processes between the holes and this electronic system.
Very well. Are there more questions? I wanted just to make a comment, which is something that we typically see when we perform calculations, that a short wire for us, theory people, is a wire of 1 micron. Long one is 3 microns or so, no? Like you were putting in your...
Yeah.
So this means that typically, at least from these theoretical calculations, basically all wires in experiments are short for
yes.
us. Okay, yes. Okay, very well. So,
okay, thanks.
Thank you very much. And we go to the next speaker, who is Ruben Seoane Souto at Lund University in Sweden. And he will be talking about revealing non-abelian statistics of Majorana bound states using charge transfer-based operations. So please, Ruben.
Yeah, okay, thank you for the introduction. So can you see my screen?
Yes.
Yeah, perfect.
Okay, so thank you for the introduction and allowing me to present my results in this very nice conference. So I'm going to present how to demonstrate Majorana non-abelian statistics using a quantum dot coupled to a Majorana wire, similar than in the previous talk. So I will start with introduction, and well, we have seen several times this week and actually early today that topological superconductivity can be engineered at the interface between semiconductors and superconductors, and that these topological superconductors host the Majoranas at the end, which are very exotic and interesting quasi-particles. And the main ingredients are superconductivity, magnetic field, and spin-orbit coupling. So this was firstly proposed by Yuval Orek and Roman Luchin in 2010, and collaborators. And the first evidences of these Majorana bound states were reported 1 year after in the group of Copenhagen as a robust zero bias peak that sticks to zero energy. So further evidences follow in the next years, showing that the scaling of the zero bias peak, and actually the quantization of the zero bias peak at very small temperatures, the closing and the reopening of the superconducting gap, which is interpreted as a transition between the trivial and topological regimes, the transition between 2e to 1e periodicity in Coulomb blockaded islands, also interpreted as a transition between trivial and topological regimes, and the exponential protection of nanowires as a function of the length. And there are some other evidences such as non-local conductance, interferometry, absence of zero pi transitions, but still many of these phenomena can be explained through a trivial Andreev bound state, very close to zero energy. So really one of the major challenges in the field, I believe, is to demonstrate non-abelian statistics, which will be the smoking gun of a topological origin of all these phenomena we are observing. So here I'm introducing non-abelian statistics. So let's imagine we have two Majoranas on the left and two Majoranas on the right. And actually, if we fuse the Majoranas on the left, meaning that we put gamma 1 very close to gamma 2, the non-local state will collapse to a state with a well-defined parity, which can be either 0 or 1, meaning that the non-local state has an even or an odd parity. So if we now braid gamma 2 and gamma 3, and we start from a state which is 0, 1, for example, the final state after this braiding will be a superposition between 0, 1 and 1, 0. And actually, this has been proposed to be used for quantum computation. Let me say that in principle, this braiding in real space may require to control nanowires in a very accurate way, using usually several or many gate electrodes, and that might be a hard approach to begin with. So for that reason, people has developed some effective way of demonstrating non-abelian statistics, and I will focus on one of them, which is based on charge transfer-based operation. So this is the device I will be focusing on during all the talk. So this is a quantum dot coupled to two topological superconductors. And this is the spectrum. And we can imagine that the energy on the quantum dot can be tuned adiabatically from very deep below to above the superconducting gap. And then if we do it in another adiabatic way, there will be a probability that this electron ends up in the left or the right Majorana. So if we start with an electron in the quantum dot and a state which might be 0, 1 for the left and the right Majorana pairs, we will end up in a superposition between 0, 0 and 1, 1 after the operation. So let me compare a braid operation with a charge transfer-based operation. So starting from 0, 1, a braid operation leads to a superposition between 0, 1 and 1, 0, while the charge transfer-based operation leads to actually a superposition between 0, 0 and 1, 1, meaning that the parity, Majorana parity, is different in the charge operation than in the braid operation. If we want to recover something similar to the result of the braid operation, we need to actually remove one electron from one of the sides. So it means to perform a second charge transfer-based operation, where now we disconnect one of the sides. And actually we get a result which resembles the braid result, but it is actually slightly more general because we can tune the value of TL, TR, and actually the phase between both. So this also means that this charge transfer-based operation is not protected by topology. And this raises the question, so how efficient can we do these charge transfer-based operations, and how undesired effects affects these operations? Well, before addressing these questions, let me say that these charge transfer-based operations can be proposed to demonstrate Majorana non-abelian statistics in 2011 in this article by Carsten Flensburg, where he proposed actually 4 Majorana bound states coupled to 3 quantum dots. And actually, non-abelian statistics can be demonstrated if 2 sequences of charge transfer-based operation lead to different results, and the other difference between these sequences has to be the order of how these charge transfer-based operations are performed. So let me say that if these states are trivial instead, the result of the upper row and the lower row will be exactly the same. With that, I'm finished with introduction, and let me introduce my model. So this is a sketch again of the system we are interested in. So there are 2 topological superconductors coupled to a central quantum dot, whose energy can be tuned using a local electrostatic gate. And we consider that the phase difference between the left and the right topological superconductor can be tuned using, for example, a magnetic flux through a superconducting loop. The Hamiltonian is given on the left, where the quantum dot is represented by a spinless electron level. The left and the right Majorana wires are described by a simple Kita-EF change, where we consider that the chemical potential is at 0 for simplicity. And this is the tunneling between the left and the topological superconductors and the quantum dots. And let me say that we consider that the quantum dot level energy is tuned for very far below to really above the superconducting gap. And the important parameter here is the slope around the superconducting gap, which is considered to be constant. And this is the relevant parameter that will determine the adiabaticity of the process. Let me say a few words about the formalism. So this is the only technical slide I have. What we do is to project the state of this non-local fermion as a function of the time, meaning counting the electrons that have been transferred between the quantum dot and these two Majorana fermions. And this is done through a so-called counting field, which is a fictitious field that is used to actually count the number of electrons. And let me say that with this regards what happens to the continuum, because if an electron ends up in the upper continuum, it does not affect in principle to the parity of the lower Majorana bound states. So this is the main ingredient in my theory, which is the generating function. And well, this is a kind of a definition, and this is the way we compute it. Well, this G naught is describes the quantum dot, and sigma describes the coupling to the topological superconductors. And this coupling can be decomposed into two different quantities, one describing the coupling to the Majorana bound state and the other describing the continuum. And actually the counting field enters only in this first part here. At the end, what we get is what we are interested in is the parity change probability of the Majorana bound states, meaning what's the probability that an odd number of electrons have been transferred between this quantum dot and either the left and or the right Majorana bound states. And this will tell us how the joint parity of the left and right Majoranas changes. So let me start with the results. First, I will focus on the operation time scale, and this is summarized in this slide here. So in the main plot here, I'm representing the operation time scale, which is actually determined by 1/r, so it's proportional to this 1/r parameter, where small means fast and high means adiabatic or slow. And I'm representing that as a function of the phase difference. And then, as you see, for different values of P of the probability of parity change. As you see, the operation time scale is maximized or can be maximized actually for phase difference equal to pi, where the two lowest eigenstates are actually degenerate. And they grow up and actually diverge close to phase difference equal to 0. And that can be understood by looking at the lowest energy states as a function of the level position. And this is represented here in red and blue, where these dashed lines are the excited states. So by just sitting down at a given a phase difference. So for a given phase difference, these two eigenstates are actually not degenerate, and this is a problem because if we initialize the system in a state which is a superposition between these two eigenstates, after the charge transfer versus base operation, we will follow this line adiabatically, and we will end up at this point accumulating some given so undesired dynamical and geometrical phase, and this will result in oscillations on the parity, so which are represented here. So this is the parity of the left Majoranas in red and the right Majoranas in blue. And as you observe, as we ramp up the level, they exhibit some oscillations at short time, and there are actually some long time oscillations due to a finite energy of the final energy of the quantum dot. And this would mean that actually the final state of the system depends on timing. And this is not something we really want in a topological system. We want it to be as robust as possible. So this can be solved by tuning the phase difference accurately to phase pi, where actually the two lowest eigenstates are degenerate. And this is the time evolution for a ramping up of the level, where we see that the system evolves from 1, 0 to a superposition to 1, 1 and 0, 0. And actually the final state does not depend on the details of how the operation has been performed if it has been adiabatic. Okay, this is a very nice picture, but up to here I haven't considered the effects of temperature. So the effect of temperature is basically to break Cooper pairs and to excite quasi-particles from below the superconducting gap to the continuum above. So there will be some finite available states below the superconducting gap here. So actually, if we ramp up the level in an adiabatic way, there is a risk, there is a chance that this electron will end up on the lower continuum, either the left or the right. So we lose the electron and the operation will fail. This means that we have to go faster than this relaxation rate here, this gamma C. And this is illustrated in this graph here, where I show the probability that this electron ends up either on the left or on the right Majorana as a function of the rate. And note this is in the logarithmic scale. So we see that these curves exhibit a maximum when we start to approach the adiabatic regime, and then it exhibits a plateau and then a decay for a very small rates, meaning that this process is taking place. And actually, it's very interesting that for the lowest temperatures, there is a very wide plateau of several orders of magnitude. So what we did is just take realistic numbers for the operation time scale, and it happens that taking realistic temperatures and a gap which is half of the aluminum gap and a realistic value for gamma, it turns out that these operations can be done in the picosecond to nanosecond regime. So let me say that this is not the full story. So there are some other effects that will affect these boundaries. So for example, if we are in the short wire regime, meaning that there are couplings between the Majoranas in the same wire, we need to go faster than this coupling. So meaning that it will affect to this boundary here. And actually, if the Majoranas are not really localized at the end of the wire, that might affect to the other boundary here. But still, there are 3 orders of magnitude, so we expect that there will be a wide range of time operations where this kind of operations will succeed. So let me go to the phase issue. So up to now, I have been only focusing on the values of A and B of the final state. But the question is there an accumulated dynamical phase after the protocol? And that we can estimate using a 2-step protocol. So in the first step, we ramp up the level at a given rate. And then after some time, we ramp up the level at a totally different rate. So if the initial and the final state are similar, it means that there is no accumulated dynamical phase. And actually, the difference between the initial and the final state might be used to quantify what's the accumulation of these dynamical phases in the system. And this is actually represented here. So on the left, I show the parity change as a function of the time. So first, we ramp up the level, so the electron is transferred to the quantum to the Majoranas. So the probability goes from 0 to 1, and then it goes from 1 to 0 when the level is ramped down. So I would like to note that there is some small difference here due to non-adiabatic effects only. And the parity of the left on the right Majoranas exhibit a similar behavior. So if we start from a state which is 0, 1, we go to a superposition between 1, 1 and 0, 0, which is what we wanted. But then when we return back, the system returns back to the same initial state. And let me say that these results were done for a phase difference equal to pi. And actually, if one considers small deviations to this phase difference equal to pi, errors here will depend linearly on the small deviation away from pi. And with that, I would like to finish. I hope I have convinced you that charge transfer-based operations are realistic proposals or alternatives to demonstrate non-abelian statistics or Majorana fermions that can be performed actually in the nanosecond to microsecond regime for realistic parameter values. And actually, the important parameter to be controlled here is the superconducting phase difference between both sides. So there is still the open question about the effects of Coulomb interaction in the quantum dot, the spin degrees of freedom, possibly consider more complex geometries, but I would say one mainly open problem is the problem of detecting the outcome of the process of the operation. And with that, let me thank my collaborators, Martin, Karsten, funding, and thank you for your attention.
Thank you very much, Ruben, for this wonderful talk. So it's time for questions.
Maybe I have a question.
Very well.
So for the when you calculate the dynamics in the presence of quasi-particle poisoning in your model, you are only considering the four Majoranas. I mean, your low energy Hilbert space is only composed by four Majoranas, but in real life, you typically have other subgap states in the system. So have you considered the role of, or estimated the role of such subgap states, and whether this, you know, these non-adiabatic processes that you consider may change the dynamics that you are calculating?
Yeah, right. That's a very interesting question, Ramon. Thank you for that. So we expect, so actually we need to go much slower than the time scale dictated by 1 over delta, which is, delta is the topological superconducting gap. But if there is in gap states, we probably need to go slower than 1 over the energy difference between these two lower, so between the Majorana bound state and the other subgap state. And that will actually affect quite a lot the boundaries of the optimal operation time scale.
Yeah, thank you.
I have a related question, which is if these Majorana bound states are, again, like quasi-Majorana, so basically they are zero modes, but still there is a overlap between them, and somehow we still, the wires are not in the topological region because this happened before the topological phase transition. Your study would be similar, no? The results would be similar, or is there something very specific about the topological state that is going to protect further your operations more than the wave function overlap?
So may I rephrase your question? You are asking what's happening if instead of having Majoranas, we have another kind of subgap states or trivial states or something like that. Is that correct?
Yes, exactly, but with a certain amount of non-locality.
Yeah, okay, so I think, let me go back. Okay, one thing is the protocol, which is one very interesting question. The other thing is if it can be used to demonstrate non-abelian statistics. Regarding the protocol, I would say there is no difference if the Majoranas are Majoranas or quasi-Majoranas or zero energy Andreev bound states regarding one single charge transfer-based operation. But however, I want to say that actually, if we do a protocol like that, where there is four actually charge transfer-based operations, the result will be similar if the states are topological or topologically trivial, meaning that these two set of operations will lead to the same result if they are trivial. Does it answer your question?
Yes, yes, yes. Yes, very well. Okay, very interesting. Let's move on because we are a little bit, we have a certain delay. Thank you very much, Ruben. And now we go to the next speaker, who is Gabor Szentesi at Eötvös University in Budapest, Hungary, who is going to talk about parity to charge conversion for readout of topological Majorana qubits. So please, Gabor, I give you the floor.
Thanks for the introduction. Okay, I will share my screen. Okay, so today I would like to talk about our recent paper, parity to charge conversion for readout of topological Majorana qubit. And in the second part of the talk, I will talk about our recent work, which is also done by Andreev. So, as everybody knows in this section, if we have a semiconducting wire with strong spin-orbit coupling, and we put this wire on an SWF superconductor, and we have some external magnetic field, we believe that we have Majorana zero modes at the end of the wire. If these Majorana modes are far enough from each other, there's no overlap between them, we have a two-fold degenerate ground state. One has an even parity and the other has an odd parity. The difference between these two ground state is a strange fermionic excitation because it's a non-local excitation which has only contribution at the ends of the wire. So the basic question of this work and also in this presentation is how can we read out the ground state? So how can we distinguish between the even and the odd parity ground state? Or with other words, how can we read out the joint parity of the Majorana modes? So the basic idea is well known from the literature. So we need an auxiliary quantum dot, which is coupled to the Majorana modes. And the basic concept is a parity to charge conversion. So somehow we would like to transfer the parity information of the Majorana wire to charge information of a quantum dot. We can do it in a static way. So in the static way, the tunnel amplitudes are constant, not varied in time. Or we can do in a dynamic way. In a dynamic way, we switch on a tunnel pulse on the tunnel barriers, which induces a charge Rabi oscillation between the wire and the quantum dot. After the parity to charge conversion, we need to measure the charge of the quantum dot. There are many techniques, so I listed only a few. So maybe the quantum dot is capacitively coupled to an LC circuit and we measure quantum capacitance, or there's a quantum point contact close to the quantum dot and we measure the current of the quantum point contact. So in this presentation, mostly I would like to talk about this dynamical way of parity to charge conversion. And I would like to talk about the measuring with quantum point contact. Okay, so a few words about the theoretical background of this work. So we would like to model this semiconducting wire on the SWF superconductor. So we would like to focus on the most simple way of this modeling, and this is the Kitaev chain. We use the Hamiltonian of the Kitaev chain. We have on-site energies, normal hopping between the neighboring sides, and some superconducting term. We are focusing on the regime when the on-site energy is 0 and these two hopping amplitudes are the same, because in this case we have a two-fold degenerate ground state, an even one and the odd one. For the readout, we need an auxiliary quantum dot for the readout, which is coupled to the first and the last side of the Kitaev chain. For simplicity in the figure, we bend the chain, but it's not important. Okay, and we have some symmetry tunneling. So these two tunnel amplitudes are the same, and we can also vary these tunnel amplitudes in time. So the question, how can we make the parity to charge conversion in this system? So here we should switch on an appropriately chosen square path on the tunnel barriers. And the square path induces a Rabi oscillation between the wire and the dot. So let's see the details. So for example, if we have an even 0 state, this is the initial state. Even is the ground state of the Majorana wire, sorry. And 0 is means there is no electron on the dot. After Rabi cycle, this state evolves to the odd one state. So there is a Rabi oscillation between these two states. So it means after a Rabi cycle, one electron is funneled out from the wire to the dot. Okay, in the other case, when the initial state is the odd ground state, nothing happens, there is no Rabi oscillation. So we can make the parity to charge conversion, because if initially we have an even ground state, after the process we have one electron on the dot. Otherwise, when the initial state is the odd ground state, there is 0 electron on the dot after the process. So finally, we need a strong measurement, and we measured what was the ground state of the TTF chain. Okay, here we can see a quite busy plot about this Rabi oscillation. So I have plotted the dot occupation as a function of path duration. So here we can see these horizontal lines which belong to the odd ground state. Here there is no Rabi oscillation, so the occupation number of the dot remains 0. Here we can see a nice, almost complete Rabi oscillation for the even ground state. And we also see that if we increase the strength of the path as a shorter but stronger path, it's also a Rabi oscillation, but an incomplete Rabi oscillation, so it doesn't go up to 1. There's a small difference, and this difference will be the parity readout error in this readout chain. The reason of this incomplete Rabi oscillation is quite simple. We have some high energy state in the TTF chain, and because of the strong paths, we have some leakage from the subspace to the high energy state. Okay, so let's see the parity readout error as a function of the path strength. So the right-hand side of the plot, as already discussed, so if we increase the path strength, the leakage will be dominant. So we will see this increasing trends on this curve. Okay, what about the left-hand side of the plot? Here we see also very large parity readout error. And the reason is the slow charge noise, because we take into account a noise which was modeled by quasi-static Gaussian on-site noise. And this also gives some contribution to the parity readout error. And that was the reason. The reason that if we have some charge noise, it detunes the energy of the quantum dot. So we have a Rabi oscillation between two states which are not in resonance. So these are not complete Rabi oscillation, and therefore we have some contribution to the parity readout error. So if you would like to summarize this plot, we can say that, okay, we have some optimal path strength somewhere here, and there's a corresponding optimal parity readout error. We can make a rough estimation with realistic parameters. So for example, I take into account 1 micro EV for the charge noise and 200 micro EV for the superconducting gap. And as a result, it gives a very nice value, 0.5% for the parity readout error. Okay, on the right-hand side, we have plotted the optimal parity readout error, so the lowest value of the parity readout error as a function of the length of the TTF chain. And we can see a saturation on this plot. So increasing the chain length doesn't improve the optimal parity readout error. And the reason is that we have a hybridization of the Majorana zero mode through the quantum dot, and increasing the chain length, which is in the other direction, has no effect on this hybridization through the quantum dot. So we have other problem with this model, which is the fine tuning, because we need to fine tune many parameters during this process. So one is the on-site energy of the quantum dot, because it should be resonant with the wire. The other problem is the path. We should control the length of the path, the shape of the path, And we also need symmetric tunneling, so at every time, these two tunnel amplitudes should be the same. So how can we solve this problem? So maybe we should shift to the static way of readout, which means there is a constant tunnel amplitudes which are connected between the ends of the wire and the dot, so they are not really in time. And we know that the dot occupation, so the occupation of this dot, depends on the joint parity of the Majorana. So there is a different occupation number for the even ground state and for the odd ground state. So if you would like to distinguish, we should measure the number of electrons on the dot. So one idea is you should use a quantum point contact and measure the current of the quantum point contact, which depends on the number of electrons on the dot, so for example, due to the Coulomb interaction. So here we can see a sketch for the outcome of a measurement. So this is the probability density function, and here the probability density function of the current of the QPC, so the quantum point contact. We see nice Gaussian curves, one for the odd ground state and one for the even ground state. We can easily distinguish between them with a simple likelihood method. So if we measure a current value which is above this threshold, we can say this is an even ground state, and if we measure a current which is below this threshold, this will be an odd ground state. Unfortunately, we have some overlap between these curves, so we made some mistake with this maximum likelihood method, and this highlighted area under the curve will be the readout error of this model. Okay, so the next step, we would like to model the quantum point contact because it's a difficult construction. So how can we make a simple minimum model? And the way that we replace the quantum point contact with a double quantum dot, which has one electron, and the tunnel amplitudes in this double quantum dot depends on the number of electrons on the dot. Okay, and how can we mimic the behavior of quantum point contact with this double quantum dot? So we use this sequence. So first, we initialize one electron on the bottom quantum dot. After that, we wait time, which means we have a half-Rabi oscillation, a half-Rabi cycle. So it's almost 50-50% that the electron is in the bottom or in the top quantum dot. Next step, we make a strong measurement. So we measure this electron is transferred or not. So, and we store this information, which is 0 or 1. And finally, we close the circle and go back to the initialization. So let's collect the observation. So first, interesting observation was the back action. So while we measure the current with this double quantum dot, there's a back action to the measured system, which is the wire plus the dot. So initially it was in its ground state, but if the time is increasing, so we do the cycles, do the sequences, we have found fast jumps to excited states, and after that is also fast jumps back to the ground state. So these are quantum jumps, and the related phenomenon is the quantum Zeno effect. And other interesting things was that we need relaxation in this model, because without relaxation, we can't reach a small value of a readout error, even if we increase the length of the measurement. So we need some relaxation, and if we have relaxation, then increasing the length of the measurement, we can reach an arbitrarily small value of the readout error. Okay, so finally, I would like to summarize this work. So I talk about Majorana wire and how can we read out the parity information of this Majorana wire. The basic concept was the parity to charge conversion. So we convert the parity information of the Majorana to a charge information of a dot. We focused on the dynamical wave and we switched on some pulse on the tunnel barriers, or a static wave when it was a constant in time. Both cases, we found we can reduce the error with longer and longer chain. In a dynamical setup, we don't need charge noise, but if we have charge noise, it has some significant error. But fortunately, we can reduce the error with optimizing the pulse strength or shape. Okay, but in a static waves, when we use this quantum point product, the interesting thing was that we need the relaxation because without relaxation, we can't read out the ground state of the Majorana. Okay, and finally, I would like to thanks for your attention.
Thank you very much, Gabor. Now there is one question in the chat that from Sunhun Park, who says, why is there no Rabi oscillation for odd zero state? Is there
odd
any
zero?
Odd zero state?
Okay.
Yeah. Is there any physical reason for that?
So the reason is we choose a symmetric tunneling here. So both tunnel amplitudes are the same. So in other case, we also can find Rabi oscillation if these two tunnel amplitudes are different. But when they are the same, we can find a Rabi oscillation in this case.
I see, very well.
So here is a destructive interference between the two tunnelings from the beginning and from the end of the wire.
Very well. So more questions, people? I just have a small question. So can you elaborate a little bit more why this Zeno effect that you were mentioning happens?
So, the Zeno effect is this is under process. So we are working on that. How can we understand this quantum Zeno effect? Because it is the Zeno effect is due to the continuous measurement. So we make strong measurement and somehow we fix the ground state of the of this wire and dot system.
I see. Mm-hmm. Very well. So thank you very much, Gabor. Wonderful talk. Time to move on. Our next speaker is Thibaut Jean-Curie. I don't know if I'm pronouncing it correctly, from the CNRS in Marseille, France, who is going to talk about giant shot noise from Majorana zero modes in topological tri-junctions. So,
okay, thank you, and hello everyone. Hello. So first, I would like to thank the organizer to give me the opportunity to present this work. And also I'm happy to have a conference because we have been working from home for a long time and it's nice to see people and to chat about physics with people. So this work has been done in collaboration with Alfredo Leiati from Madrid and the group of Reinhold Egger and Alex Zazunov in Düsseldorf. And it was done also in Marseille in the Centre de Physique Théorique in the group of Thierry Martin together with Jérôme Resch. So I don't really need to introduce the context about Majorana bound state. So we are interested here in Majorana bound state in 1D nanowire topological superconductors and to have more understanding and more proof of these Majorana bound states. So our way of doing is to study multi-terminal setup. So we have more than a simple two-terminal setup. Here we study a setup which has 3 topological superconductor nanowires. And we want to find original signatures of Majorana bound states, maybe more robust than the typical conductance peak or the 4π periodicity. And I will show that considering current correlations, also called as noise rather than simply current, is a very useful tool to this. So this is the very schematic view of the setup we are considering. So we are taking 3 topological superconductor nanowire, a central one which is grounded, and which is coupled on the left and on the right to 2 other topological superconductor. which are placed at non-zero voltage V1 and V2. And on the plot on the red here, you can see schematically the Majorana bond states at the end of each topological superconductors. And of course, at the other end, there are also Majorana bond state, but they are not really important because we consider very long nanowires. And so there is a tunneling coupling between the central endpoint here and the left or the right topological superconductors. In the rest of the talk, I will only consider the case of opposite voltage on the two topological superconductor V1 and V2. But what I will tell you won't qualitatively change if you consider another value for this voltage. As long as you are out of equilibrium, it's okay. And so why did we consider this setup with three topological superconductors? So one is a practical reason is that we know that, for example, for topological computation, if we want to mix and to braid Majorana, typically you have setup where you have at least three topological nanowire. So it's important to understand really what happens. And the other is a more fundamental reason is that when you take a simple junction between two topological superconductors, you have two Majorana. And you know that when you couple two Majorana, what you get is effectively one fermion. So then you recover physical fermion and you maybe lose a bit of the physics of Majorana. But if you consider a system with three topological superconductors, then in the middle here, okay, I have a pointer, you have those three coupled Majorana. And whatever the way you couple them, if you couple three Majorana, you will always end up with one effective fermion, one combination of the three Majorana, which will be an effective fermion, plus one effective Majorana bond state. So this means that in this system, you still have a real Majorana bond state which is present and which will strongly modify the transport properties. Okay, so we compute them, the transport properties, so the current and the noise in the system using standard technique, and I will not go into details of the technique, but we are using out of equilibrium green function formalism and solving Dyson equation to get an equation for the total green function of the system, which we compute numerically and from which we can compute current and noise. The only technical point I want to stress is that we use what is called boundary green function. So in fact, the transport can be only described by what happened at the end of each of these topological superconductors and tunneling between this endpoint here. So this can be done if you know the green function of the boundary of each of the topological superconductors, which knows everything about the dynamics inside each of the topological superconductors. So the transport is described by coupling of boundary green function of the different topological superconductors. And this object has been studied and determined in a work by Zazunov, Eger, and Levy-Yati in 2016. And this is the expression for the retarded or advanced boundary green function. So at the boundary of a topological nanowire. And you can see that it has really, it's very simple analytical formula, but on the other hand, it has all the properties we expect from a topological nanowires. So on the one hand, we have a gap with a density of states beyond the gap for quasi-particle states with a different behavior than BCS, so no BCS singularity, but a square root behavior. And on the other hand, we have this zero energy peak, so the Majorana bond state, which is also included in this green function. So this is the density of state you get from this very simple boundary green function. And okay, then we just use the known formalism to compute the current and noise. And let me start immediately by showing you the current. So this is the current from the central nanowire to the left one, so I call it I1, scaled by the transparency of the junction as a function of the voltage applied and for different values of transparency between the central nanowires and the two lateral ones from 0.2 to 0.8. And okay, the features of this curve are, okay, of course, when you increase transparency, you will increase the current. And typically you see that you have onsets of the current, which appears at delta over n, where n is an integer. And this is a behavior which is typical for what is known as multiple Andreev reflection. So here we have multiple Andreev reflection, which are modified by the fact that at zero energy, you have this Majorana bond state. So when you apply a voltage which is smaller than the gap, it's not possible for one quasi-particle to end up in the gap on the other side. But by being Andreev reflected one or several times, it's gaining energy. And at some point, it has enough energy to be transmitted to this zero energy state. And so which explains why we have this onset at delta over n. So this is the standard multiple Andreev reflection adapted to the case of topological superconductors. And in fact, so this is the result for the 3 leads case, but qualitatively, it's not so different from the case of the 2 topological superconducting case, which has been considered by a group in Grenoble in 2013, where you also have this onset at delta over n, which are easily understood. So which means that the current is not really the good quantity to look at if you want to really have unique properties for the three terminal system, and which is why we looked at the noise, so the current correlation. And this is the result for the autocorrelation, so the correlation of the current I've shown before, so S11 as a function of voltage. And here I've focused on smaller voltage, so compared to the gap, and also for different transparency, again, from 0.2 to 0.8. Okay, and this figure was really surprising, and I will try to explain you why it's surprising and why it's quite unique. So first things to notice is the scale. In order to plot this noise here, I had to use a log scale with noise, which can be as high as 100 or a few hundreds or thousands. And if you compare to the current, is always of the order of 1 in our atomic units. So this noise is huge, really, really, really large. And the other surprising feature is that the noise is increasing when we are decreasing transparency, which is quite counterintuitive. Typically, if you increase transparency, you have more current and more noise, but here it's the opposite. And the finite, the last peculiarity is that this noise has peaks, and these are huge peaks because we are in a log scale. And these peaks, again, are present for the values of the Mach onset, so delta over n, delta over 2, delta over 3, etc. So this was a surprising result, and we had to think about it for quite some time. And okay, and the first thing we want to be sure is that this is really related to the fact that we have a system out of equilibrium with 3 topological superconductors. And one way to do this is in fact to turn a knob to change parameter such that one of the lead is not topological anymore. So here I show the Fano factor, so the ratio of the current, the noise to the current. When I vary, in fact, the intrinsic chemical potential of the second topological superconductor. And you can see that as soon as I go from the topological regime to the trivial regime, the Fano factor, which is huge in this topological regime, becomes of the order of 1 for the trivial regime. And we have checked that by changing all the parameters. So in order to get these huge values of noise, you really need to have 3 topological superconductors connected out of equilibrium. And okay, so now just to summarize, really to show the qualitative difference between the 2-lead system and the 3-lead system. So here I show the current, the noise, and the Fano factor for the 2-lead case on the bottom row, and for the 3-lead case on the top row. And again, you can see that the current are qualitatively similar. There are some quantitative difference, but we have just this onset. But on the other hand, the noise for the 2-lead case is also of the order of 1. There are some features, but it stays of the same order as the current. While here in our case, we have noise which is several orders of magnitude larger. And then of course, if you compute the Fano factor, well, for the 2-lead case, the Fano factor is increasing as the inverse of the voltage. And this is just because the Fano factor reflects the effective charge, which is transmitted in the multiple Andreev reflection. And so it's proportional to the numbers of reflection, which is increasing as 1 over the voltage. But in our case, we have Fano factor, which are again, several orders of magnitude larger. So we have really something different going on, and we need to understand what happens. And okay, doing full analytical calculation in this system is really difficult because in the Dyson equation, you have, in fact, very large matrices due to the non-equilibrium and the fact that you have 2 superconductors at different voltage. So we have to make some approximation. And one approximation, which is quite natural, is what we call the atomic limit. So as you can see, the noise is very large when you go to small voltage and also small transparency. Then it makes sense to consider that the delta, so the superconducting gap, is the larger energy scale of the problem. And this means that if you take the limit of this gap going to infinity, you can neglect all the continuum with the quasi-particle state which are beyond the gap. But if you do that, then you get a very simple system where each topological superconductor is just represented as a single Majorana. And then the Hamiltonian becomes just the coupling between the Majorana of the central one, gamma 0, coupled to gamma 1 and to gamma 2, with opposite sign because we have opposite voltage, and an amplitude which is time dependent because we have voltage and we have superconductor. So this is related to Josephson frequency. So this becomes the Hamiltonian of the system. And then without going really to the details, what we can do is just by simple algebra, I can define new Majorana, which are linear combination of gamma 1 and gamma 2, symmetric and antisymmetric. And then I can define an operator which I will call D, which is a combination of gamma minus and gamma 0. And it happens that if you check it, the commutation relation of this D operator are exactly fermionic. So D is a fermionic operator. And in fact, the Hamiltonian is just the Hamiltonian for a single fermion D, which has conserved parity and with an energy position, which is time dependent as to the voltage applied. So as I said before, when we combine 3 Majorana, what we get is an effective fermion, which is this fermion D, plus another effective Majorana. But in the Hamiltonian, only the effective fermions appears. But on the other hand, the current operator from the central lead to the left one or the right one has this expression. And again, there are some parts which depend on the effective fermions, but also a coupling between the effective fermion and the effective Majorana gamma plus, which does not appear in the Hamiltonian. And the fact that the current operator has this non-trivial coupling to the zero energy state, the zero state, so this effective Majorana bond states, is the reason why we get this huge noise, because we have some discrepancy between the basis with which we want to describe the Hamiltonian, which is only the fermion, and the basis for the current, which makes appear the fermion plus the zero energy mode. Okay, and then, okay, this is a really simple Hamiltonian, so it's possible to solve exactly what happens. And so we can compute analytically the noise, the current correlation in this atomic limit. And this is the result that we get. So the main feature is that, of course, it's proportional to the coupling amplitude, turning amplitude between the leads. There is a Bessel function square which depends on the coupling divided by the voltage. So the function of the inverse of the voltage. And finally, there is this important 1/eta parameter, where eta is the intrinsic parity relaxation rates of the Majorana bond states. So this is related, in fact, to the effective width of the green function you are putting in your boundary green function. And it just represents the fact that if you have a topological superconductor, so with a Majorana bond state, it's coupled to the environment. And there is some probability that the environment will change the parity of your Majorana. And this is expressed by this parameter much smaller than 1. And so if we compare these analytical results of the atomic limit approximation to the full numerics, so this is what we get for transparency 0.2. So the red one is the full numerical result, same as before, but in linear scale as a function of voltage. And the blue one is the atomic limit. And this is the same for transparency 0.3. So what we can see, there are good points and bad points. The good point is that the overall scale of the noise is quite well reproduced by the atomic limit. So this means that we understand where these huge values of the noise come from. It's due to the fact that this noise is proportional to the inverse of the intrinsic parity relaxation rate, which is really small. And so this gives a correct envelope for the noise. And also the atomic limit seems to reproduce nearly quantitatively what happens really for very small voltage. But on the other hand, of course, the full numerics has really peaks which happens at Mach onset. And these are not described at all by the atomic limit, which is not really a surprise because these peaks are clearly related to multiple Andreev reflection because they happen at Mach onset. And the atomic limit doesn't know anything about multiple Andreev reflection because it does not consider quasi-particle. So it's not surprising, but so it would be good to have an analytical calculation which allows to really reproduce the peaks we observed and to understand why we have these huge peaks. And in fact, there is one effective way to do this. So we need to include the effect of the multiple Andreev reflection processes. And the simple point to understand is that when you have a multiple Andreev reflection process, in fact, you are changing the parity of the effective fermion D because you are changing this occupation of this fermion. So Mach processes are also contributing to the change of the parity. They are also changing the parity. So you can define the covariance time for the parity, which is due to the multiple Andreev reflection process and not to the coupling to the environment. And so the typical time between the two electron tunneling in Mach process will be simply related to the inverse of the Mach current. So this is this current I, which we can compute. And there is a factor here, which is simply the numbers of reflection in the Mach multiple Andreev reflection current. So this defines an effective covariance time for the parity due to the multiple Andreev reflection processes. And then I can define an effective parity relaxation rate, which will take into account both the coupling to the environment with the rate eta and the coupling, the action of the multiple unrest reflection, which will simply the inverse of this covariance time. And then in a very crude way to get some quantitative result, I can just consider an effective parity relaxation rate, which will be the maximum of the intrinsic one and the one due to multiple unrest reflection. And so this defines an effective parity relaxation rate, which will depend on voltage and which we can compute if we know the current. So we can compute numerically the current and then from this get the effective parity relaxation rate. And then I can use the analytical formula I had from the atomic limit approximation, but replace the the intrinsic parity relaxation rate by the effective one, which combine the effect of environment and multiple unrest reflection current. And well, this is what I get. So again, this is comparison between the full numerics in red. Okay, the atomic limit is the same as before, is in blue. And the black one is the one where I introduce effectively the effect of multiple unrest reflection current. And at transparency 0.2 or 0.3, you can see that we get nearly very good quantitative agreement between the full numerics and the one due to the simple atomic limit formula, including the effect of multiple unrest reflection. Cool. So I need to conclude. So my main message is really to show that as soon as you take a very simple system with 3 topological superconductor coupled out of equilibrium, you get a shot noise, which is really huge, which is several order of magnitude larger than what you get in a 2-terminal setup. And this is really surprising, and new, and interesting. And I've shown also that these large fluctuations are due to the presence of a zero mode, which just results from the fact that we are coupling 3 Majorana bound states. And the height of the noise is limited by the relaxation time, which is due to a combination of intrinsic parity relaxation time and multiple unrest reflection current. And also the more general message is, okay, looking at setup which are not simply 2-terminal, but with more terminal out of equilibrium, allow really to probe a unique property which are not accessible in a 2-terminal setup. Thank you for your attention.
Thank you very much. Wonderful talk and incredible, nice analytic results. So let's see. We have some questions from Pasquale Marra. We have Majorana states localized at the edges of the non-trivial phase. If the whole 3 topological superconducting system is non-trivial, how one can justify the assumption that Majorana states localize at the center of the junction?
Okay, it does not. I have not supposed that they localize in the middle. The point we have here, these 3 topological nanowire. So at the end of each of the nanowire, there is a Majorana bound state. So it's really at the boundary. So I am understanding the question correctly. So I'm not supposing that there is a Majorana in the middle, but they are just, we are just starting from uncoupled nanowire, which each have a Majorana at the boundary, and then we are introducing coupling between them. Then we have an object which is these 3 Majorana bound states coupled with tunneling.
Yeah, I think, yeah, that's what he had in mind. Well, why the 3 Majoranas localize at the center? There is no boundary there.
Well, each nanowire has a boundary.
Okay, yeah.
We have to,
yeah, you have to imagine they are
really, we have
wires. Yeah.
Mathematically, we start with semi-infinite nanowire here. So each of the nanowire is semi-infinite. So they are really boundary. Here there is a boundary. So they are really, each of the nanowire has a boundary.
Okay, they are not in contact. I get it very well. So he's satisfied. And then there is another question by Sun Hoon Park. Is the small intrinsic parity relaxation also important for the noise in the 2-terminal geometry?
Yeah, much less, because you don't, the limitation, the values of the noise in the 2-terminal geometry, you cannot really see the effect of this parity relaxation time in the two-terminal case.
So there is some intrinsic term, but it's but you cannot see it, or?
Yeah, the parity relaxation rate is always there, but you don't see this effect in the two-terminal case. It is not the limiting factor for the noise in the two-terminal case. But on the other hand, if you go to the three-terminal case with very small voltage and very small transparency, there you can see the effect of the intrinsic.
Very well, very well. So wonderful talk. Thank you very much. And we go to our next speaker, who is Chung-Xiao Liu from Delft University in the Netherlands. And he's going to talk about Josephson current via an isolated Majorana zero mode. So we connect with Chung-Xiao.
Yeah, can you hear me? And can you see the
yes.
keynote? Yeah, okay, good. Yeah, thanks for the introduction, and also thanks to the committee for organizing this nice conference and colloquium. So hi everyone, I'm Chung-Xiao Liu. I'm from QTech in TU Delft, the Netherlands. So today I'm gonna talk about our recent work, Josephson current via a isolated Majorana zero mode. So it's in collaboration with Berna and Michael. And you can find this work on arXiv. So first for the motivation, although so far most of the experimental studies of topological superconductor and Majorana zero modes are focusing on normal superconductor junctions, tunnel spectroscopy, there are also many proposals for Josephson junctions. For example, the 4-pi Josephson effect is predicted in junctions between two topological superconductors, among many other interesting phenomena. And also people have proposed, have considered the junction between a conventional and a topological superconductor junctions. So for example, you can either look for signatures in the IV curves in non-equilibrium system with bias voltage in the conventional superconducting lead, or you can look for the DC Josephson current signatures in the same STS devices. And recently it has been proposed that making use of two conventional superconducting lead and topological superconductor island in between, you can do quantum information processing with Majorana zero mode using the Josephson current. So today, in this talk, we are gonna focusing on the Josephson junction between a conventional and a topological superconductor, where a Majorana is localized in between. And a key observation on the proposals so far is that there's always an assumption of time reversal symmetry in the conventional superconducting lead. But in realistic experimental setup, if you want to say induce topological superconductor, a magnetic field is always applied globally, so that the time reversal symmetry in the conventional superconducting lead is inevitably broken. So the question we ask is, so how would this time reversal symmetry breaking in the conventional lead affect the DC Josephson current in this say conventional topological superconductor junctions? So the model Hamiltonian we use is the one-dimensional hybrid system between spin orbit coupled semiconductor and S-wave superconductor. So we assume that, say, we can tune the parameters for the left and the right superconducting leads independently. For example, they have a split gate so that we can tune the chemical potential in each lead. And also we focus on a tunnel junction between in a tunnel junction so that the current phase relation for the Josephson current is a sine function of the phase difference. Here, IC is the critical supercurrent, and phi naught is the anomalous phase shift in the current phase relation. And these two quantities will be the focus for my discussion later on. And since it's in a tunnel junction, we can use perturbation theory to understand the physics and do the calculations. All right, so first I want to talk about the supercurrent in a conventional Josephson junction between two trivial superconducting lead. So the supercurrent can be induced by the tunneling of Cooper pair, and the tunneling process of the Cooper pair can be understood in a two-step process. So first, a single electron, for example, spin up, will tunnel from the left lead to the right lead. And since now the two electrons are unpaired, they will excite the quasi-particle excitation in both leads. And in the second step, the spin down electron would also tunnel from the left to the right, so that the two electrons will make up a Cooper pair again and in the condensate, so that it finishes the process of a Cooper pair tunneling. And the similar process can happen for a reversed order of tunneling electron spin, with first a spin down electron going from left to right and then followed by a spin up. And all these contributions will add up together to form a finite supercurrent in the conventional Josephson junction. And there is a relation between the critical current for the supercurrent and the normal conductance. It's the Amber-Gauker-Baratov relation, right? Next, we look at the similar process between a conventional superconducting lead and a topological superconductor. Now there's a zero mode. There's the Majorana zero mode localized at the junction between the two superconducting lead. So there's another option for the Cooper pair to tunnel from left to right. So the first electron, say spin up, can tunnel into the zero mode, leaving an unpaired spin down electron. And in the second step, they form Cooper pair again. But here, a different thing from the conventional junction is that so a reversed order process, say with spin down going first, followed by spin up, would have a pi phase shift relative to the spin up then spin down because of the Majorana zero mode, and therefore such a process will interfere with each other destructively, and there's no supercurrent from, say, Cooper pair tunneling between a trivial lead and an isolated Majorana zero mode. So, and the people call this phenomenon supercurrent blockade. And one thing I want to emphasize is that although in the description of the physics picture, I keep saying spin up and spin down, but actually the spin is not necessarily a good quantum number in the system. But the key point is that as long as the trivial superconducting lead is time reversal invariant, then this destructive interference would always happen, and making the Majorana supercurrent blockade. So, and we have proved that using the Anderson's theorem. Okay, so then the next question is, so if there's no supercurrent signal from an isolated Majorana zero mode, then how can we lift this this supercurrent blockade? Because it's always difficult to say we have detected the presence of Majorana zero modes by seeing nothing in the experimental signal. So there are a couple of proposals already there, in the existing literatures. For example, you can consider a more complex devices with a quantum dot in between. And to break the pi phase shift between the two processes. Also, people have considered the superconducting lead to be finite length, so that the two Majoranas from two ends of the.
¿Cómo estás? Soy Cristian Parodia para utilizar debajo, donde estoy mostrándote ahora mi mapa.
Excuse me, there is a problem. Someone doesn't have muted his microphone. Please, everybody mute your microphones, please, during the talks.
Yeah, okay, good.
Please continue, thank you. Sorry.
Sure, no problem, no problem. So in the second proposal, people consider finite length nano topological superconductor, so that the faraway Majorana can also has some weight in wave function near the junction, so that the Cooper pair can tunnel into the second Majorana. But here in our work, as I mentioned in the beginning, what we consider is a finite Zeeman field in the trivial superconducting lead. And this explicitly breaks the time reversal symmetry in the trivial lead, so that it should give some finite contribution for the supercurrent due to Majorana zero mode. So a cartoon picture here is that the quasi-particle continuum in the trivial lead of with spin up and spin down split by a Zeeman energy, and the tonal amplitude for spin up followed by spin down, and the spin down by spin up are different now. So it will give a finite contribution, a finite Majorana-induced supercurrent proportional to the strength of the Zeeman field in the trivial lead. Also I want to mention that so there's also an angle dependence of the direction of this Zeeman field. Say, suppose the Majorana zero mode has some spin polarization, say spin up, and if the Zeeman field in the trivial lead is parallel or anti-parallel with this direction, then the Cooper pair tunneling is still blockaded, because you want spin up and spin, both electrons with spin up and spin down tunnel there. But now the Majorana wave function, if it has only spin up, then only and then the electron with spin down will be blockaded as well. So not only is the supercurrent proportional to the strength of the Zeeman, it also has some angular dependence there. Okay, so having understand the intuitive picture of Majorana-induced supercurrent, we now turn to the numerical simulations for a more realistic model, which is the semiconductor-superconductor one-dimensional nanowire. So for the numerical calculations, now we can include not only the Majorana contribution to the supercurrent, we also will automatically include the contribution from the quasi-particle continuum above the gap. So as a starting point, we consider the case where the the Zeeman field in the trivial lead is still absent. So, and the Zeeman field is applied only in the topological superconducting side. So this is not a realistic situation perhaps, but we start from this to make sure that what we understood, the supercurrent blockade picture was correct. And this is the resulting critical current as a function of the chemical potential and the Zeeman field, both only in the right lead. The white dot denote the phase boundary between the topological and the non-topological superconductors. And we can see that as shown in the cut lines in the on the right. So the critical current will monotonically decrease with an increasing strength of the Zeeman field in the topological superconducting side. And when the right superconducting lead enters the topologically non-trivial phase, the critical current will reduce significantly. And here in this case, there should be no contribution from the Majorana zero mode. And the second, we consider that the Zeeman field is applied globally in both trivial and the topological superconducting lead. And we can see that now the critical supercurrent behavior is very different. You can see that instead of monotonically decreasing with the strength of the Zeeman field, now the critical current will increase in the topological regime due to the presence of Majorana and its contribution in the presence of finite Zeeman field in the trivial lead. So in the right panel, the dashed line is only the Majorana contribution to the supercurrent. So you can see that it approximately increase with the strength of the Zeeman field linearly. So that's a very interesting signature characteristic of the presence of Majorana zero mode. And we hope that experimentally we can, people can find such a signature in the search of Majorana zero mode. And next we consider the scenario of so instead of the Zeeman field applying parallel to the nanowire, we now assume that there's a finite Zeeman field also in parallel to the spin orbit field. So what's interesting here is that it will break one subtle symmetry, the chiral symmetry in the semiconductor superconductor nanowire, and giving rise to anomalous phase shift and anomalous supercurrent. That is, even there's no phase difference between the two superconducting lead, there can be a supercurrent flowing between them. So we plot both quantities in terms of the chemical potential and the Zeeman field in the right lead. And you can see that once the right lead enters the topologically non-trivial phase, both the anomalous supercurrent and the anomalous phase shift will increase abruptly due to the presence of Majorana zero mode. So we argue that this can also be served as one possible signature for the presence of Majorana zero mode. Okay, so I probably will stop here with the conclusion page. So in summary, we have studied the Josephson junction between a trivial and a topological superconductor. And we argue that the time reversal symmetry in the trivial superconducting lead is essential for inducing some Josephson current signals from an isolated Majorana zero mode near the junction. And this signal can be, say, normal supercurrent or anomalous supercurrent and phase shift. Okay, thank you for your attention.
Thank you very much for your talk. Very, very interesting. Let me put some. Okay, so it's time for questions, please. I see there is no questions from the chat. So experimentally, what would be, I mean, what you need different from the experiments that are already underway? So what would you say is the experimental status regarding this kind of system?
Sorry, what is the question? So you are saying, yeah, I think the geometry is not difficult to fabricate in the laboratory.
Yeah, that's basically my question. So you need one of the parts of the wire has to be trivial.
Oh yeah. Oh yeah, I think I should mention it earlier. So in our model, we tune the chemical potential in the left lead to be say large, so that even with the same strength of Zeeman field in both sides of the lead, the left lead is still in the trivial phase. And experimentally, this can be tuned by, say, gate. But I have to say that experimental situation will be more complicated since you probably would have many subbands.
Yeah, well, yeah,
that's not under control. So yeah, we are still, say, continue to look at more realistic and complicated cases, say in 2D or 3D.
Okay. So there is a question from Kanster Flensberg. How would a spin-orbit interaction in S change the result?
How will
how the spin-orbit interaction in the superconductor change the result?
Spin-orbit direction, you are saying. I think so as long as the Zeeman field is perpendicular to the spin-orbit field, it has no difference. Say the spin-orbit field is along y direction, sigma y direction, then the Zeeman field along sigma z or sigma in the sigma z and the sigma x plane are equivalent. This to get anomalous phase shift or anomalous supercurrent, you need to have a Zeeman field component in parallel to this spin-orbit field to break the chiral symmetry. Is that the question?
So Karsten continues saying, but different spin-orbit interaction in S with respect to the TS, so from the trivial S to the topological S. By the way, Karsten, if you want, you can unmute your microphone and, and ask directly. But his question is a different spin-orbit interaction, let's say, in the two sides.
I see. I guess for
can you hear me?
Yes.
Yes.
Oh, okay, I was just wondering whether this thing that time reversal forbids supercurrent between S and TS, is that true also in presence of any kind of spin orbit?
Direction, you mean?
Yeah, any direction in barrier or in the trivial superconductor, because with spin orbit in the superconductor, the Cooper pairs wouldn't be made out of Kramers pairs, which might have an overlap with where both partners have an overlap with the Majorana state.
Yeah. I think actually in the appendix of the archive, I had a more rigorous proof. I want to say that, where is it? I want to say that, yeah, although I say it's a spin up and spin down, but in reality, it's more like a Kramers pair.
Yeah.
So no matter what the direction of the spin orbit coupling, you cannot say it's spin up or spin down, but you can prove that the processes will give an exact, say, destructive cancellation for if it only turns to a single Majorana zero mode.
Okay.
So I think it's general. Spin is not necessarily a good quantum number in this process.
Okay. Yeah. Okay, that was my question. Yeah.
Thank you.
Okay. Thank you very much, both of you.
Thank you.
And well, it's a bit late, so let's go to the next speaker, who is Miquel Rouco from San Sebastián in Spain, who will talk about gap inversion in 1D Andreev crystals. So please, Miquel, I give you the floor. So you have to...
Okay, you can hear me now?
Yes.
Okay. Okay, so thank you for the presentation. I'm Miquel Rouco, and thank you for your assistance as well, and thank you the organizers for this nice conference. And today I want to present a work that I did in collaboration with my co-supervisors, Sebastián Bergeret and Ilya Tokatli, both from San Sebastián as well. This work is entitled Gap Inversion in One-Dimensional Andreev Crystals. We recently uploaded it to the archive, so here you have the reference if you want to check it later. As an introduction, I first want to explain what are Andreev crystals and why did we choose this name for them. So we begin by considering a single magnetic impurity in a superconductor. To explain the nomenclature here, with impurity, I mean that it is an impurity for the superconductivity. This is that the characteristic length of this region is much smaller than the superconducting coherence length. For simplicity, we consider a quasi-one-dimensional system where the exchange field in the magnetic region is constant and collinear. And in such a system, the meaningful parameter that governs the physics of the bound states appearing here is what we know as the magnetic phase, which is proportional to the product between the exchange field and the width of the region. Just to remember, I mean, you may know that Andreev bound states appear in many kinds of junctions between superconductors, and this is just another example of them. So this problem has been widely studied in the literature, mainly in two limiting cases. On the one hand, we have the atomic case, the atomic impurity case, where the width of the impurity is much smaller than the Fermi wavelength, and then the exchange field is very localized and very strong compared to the Fermi energy. In this case, recalling the typical picture of the superconducting spectrum with the two electron hole valleys at the two Fermi surfaces, such a strong exchange field couples both valleys, and then we obtain some non-degenerate bound states known as the Giussi-Barrosinov bound states. On the other hand, we have the opposite limit, where the region is much larger than the Fermi wavelength, and the exchange field in it is weak compared to the Fermi energy. Here, the two Fermi valleys are still decoupled, and we can apply a semi-classical approximation, where we obtain degenerate states due to this valley degeneracy. And this is the way to obtain the Andreev bound states. In a recent work, we also show how these two limits can be connected. As you can see, for example, in this plot, where we fix the value of the magnetic phase of the region, and we plot the energy of the bound states for different widths of this magnetic region. So here in the plot, the left part would correspond to the Giussi-Barrosinov limit, whereas the right part of the plot asymptotically tends to the Andreev bound states. Now that we understand how the physics in a single impurity works, so we can start thinking about arranging many of these impurities, forming a chain, so that we can expect that the bound states hybridize, forming bands. This, as you may know, this idea was already considered in many previous studies, but for impurities with that exhibit Giussi-Barrosinov states, like atomic impurities, as for example in these two famous papers by Antwerp and collaborators and Pienka and collaborators, where they found some topological phases and Majorana bound states at the edge of the wire. However, little attention has been paid to the Andreev limit. So the motivation of our work was just to study the spectral properties of chains formed by these semi-classical impurities. And as each one of these impurity exhibits Andreev bound states, we call them Andreev crystals. So now I start explaining the main results of our work, in particular the spectral properties of such systems. The geometry of the chains is the following. We consider many of these magnetic regions or magnetic impurities, where inside of each region the exchange field is constant, the separation between the impurities is constant as well, and for simplicity we first considered that the exchange field among the impurities is always collinear. So such a system is described by a Hamiltonian like this one, where you can notice that we have a first order differential equation, which is the signature of the semi-classical approximation. Our plan is first to study two different types of Andreev crystals, the ferromagnetic and antiferromagnetic ones. And we take two different analytical approaches to do so. We first solve a tight binding approximation up to first neighbors, from which we obtain some simple equations and we can infer some general results. And afterwards, we also obtain the exact solution from Eilenberger equation using Green's functions, just to corroborate and verify that the general results that we obtained in the first approximation are correct. We can start by considering ferromagnetic Andreev crystals, where all the magnetic impurities are equal and all aligned in the same direction. We have a single impurity per unit cell in such a system. And in the spectrum, we obtain two different bands with opposite energies. Each of one corresponds to one spin orientation, the spin up and spin down. Here I will play a movie where you will see how changing the magnetic phase of the impurities of the chain, two bands start entering into the superconducting gap and they cross each other without interacting. So each of the bands corresponds for one spin orientation, and in general, we can say that nothing really interesting is happening here. On the other hand, we have the antiferromagnetic Andreev crystals, where we have two impurities per unit cell. And now, in the spectrum, you obtain two symmetric bands for each spin orientation. These bands now interact with each other, and therefore we have a gap around the Fermi energy that only closes for given values of the magnetic phase here. Here I show you a similar movie of the spectrum of these systems, where when we start changing the magnetic phase of the impurities, we see how two bands enter. We always have a gap here, except for a single value of the magnetic phase. This result is indeed verified by exact calculations of the local density of states of the crystal. Here I show you only the spin up component of the local density of states. On the x-axis, you have the spatial variable. And when we start changing the magnetic phase, we also see how two bands enter to the gap and they touch each other at pi halves or so. So you may have noticed that when the gap closes forming a Dirac point. And in fact, if we linearize the tight binding equations around that Dirac point near to the gap closing conditions, we obtain a one-dimensional Dirac equation where the parameter omega naught plays the role of the mass. This parameter is a renormalized energy of the single impurity bound states. And in fact, it changes sign when the gap closes and reopens again. So as you may know, a one-dimensional Dirac equation with a mass that changes its sign spatially exhibits some zero energy bound states in the area where the mass changes sign. So we can ask ourselves whether this is also happening in these systems. So yeah. What happened here? Okay. So for that reason, we considered junctions of two different antiferromagnetic Andreev crystals, where, as sketched here in this drawing, where on the left we have a chain described by impurities with magnetic phase phi L, and on the right with magnetic phase phi R. And in this kind of systems, we obtain spin polarized bound states appearing inside near the interface. And this state may lead also to some surface spin polarization. This just to show you, I show you here the local density of states of junctions between these chains, where from this point to the right, we have the right chain with a constant magnetic phase of the impurities. And for the left chain, I will start varying the magnetic phase of the impurities. And you will see how the gap closes. And when it reopens, bound state appears in the interface. This is the local density of states for a spin up. For a spin down, we would have the same, but the bound state will have the opposite energy down here. These spin polarized bound states have an effect on the surface spin polarization of the system. And to calculate it, we first have to understand how the spin polarization evolves in the single impurity program. So the single impurity spin polarization has a staircase shape like this, as we showed in the previous work as well, where the important thing is that we can only, the spin polarization can only take even values of the spin electron, the electronic spin. This is due to this Bali degeneracy that it is built into the semi-classical approximation, right? So with this result, we can easily calculate the surface spin polarization of a junction between these chains in the atomic limit. This is when the impurities are very separated from each other. In this case, we basically have many single impurity problems. And to calculate the surface spin polarization, what we do is to average over all the possible chain endings. So we may have balanced chains, or we have one unbalanced chain, the other one balanced, or so on. So we have 4 possible chain endings, and averaging over all this, we obtain that the surface spin polarization of the system, we obtain a formula for the surface spin polarization of the system in terms of the single impurity spin polarization that we know. When we start bringing these impurities together, the gap around the Fermi level remains open. So as we discussed in this last work as well, the spin polarization doesn't change, and therefore this formula remains valid for any separation between impurities. So when we plot the surface spin polarization in terms of the magnetic phases of right and left chains, we obtain a color map like this, where it is important to notice that we can obtain odd values of the electronic spin, which means that we have fractionalization of the surface spin polarization at each value. This result, in fact, is verified by exact calculations using Green's functions, where here I plotted the surface spin polarization for a single Bali degeneracy, and therefore we can obtain, we can see that we obtain half integral values of the electronic spin. So this is all. To conclude, in this work, we introduced the concept of Andreev crystals. We gave a complete study of the spectral properties of some of them. And in particular, we focused on antiferromagnetic Andreev crystals because they showed some interesting gaps that closes, creating direct points, and studied the bound states that appear in junctions between these kind of crystals. So thank you for your attention. And if you have any question, you can ask it now.
Thank you very much, Mikel, for this very interesting talk. So we have time for one question, if there is any in the audience, because we have certain delay from previous talks. Otherwise, we might discuss further this afternoon. Thanks to you and everybody. And so we have arrived to the last talk of this morning session, which is an invited talk that will be presented by Sergei Frolov from the University of Pittsburgh in Pennsylvania, in what promises to be a very exciting talk and subject. The title is Physics, Material Science and Engineering of Majorana Circuits. So please, Sergei, I give you the floor. Are you there?
Yes.
Yes.
What do you see? Do you see the
Pisa.
share or?
The Pisa Tower and the slides.
Okay, slides in a PowerPoint window or full screen?
No, it's not full screen.
Okay. Hold on, let me try again. How about now?
Perfect. Go ahead.
Yeah, thanks. Really, I've never been to Madrid. So really looking forward to it. Was looking forward to it. Well, I hope we can still all meet in near future. So it's the last talk, and I had a lot of different Zoom meetings over the course of the past month. So actually, I think Zoom is very powerful. Everybody has a microphone. Everybody can, chat, and it's kind of more direct. So I actually encourage you to interrupt and ask questions whenever. I see that I don't see the chat window anymore. Oh, yeah,
yes.
I do. So you can send chats, or you can just shout. It's all fine. Yeah, I'll be talking about the experimental situation with Majorana modes. Obviously, there are many people working on this subject. I will be using our own data, not because I'm such an egomaniac, but because then I can make bold statements and show examples from my own work, people are more calm. So first of all, I would like to thank my group. This is our socially distant group photo, recent graduation party. So we have a lot of great students, and all of them work on something related to Majorana, but also very importantly, we work with many other groups in theory, also materials growers, very important, providing us with nanowires. And it's not really providing anymore, it's really a very tight feedback loop between these two efforts. Probably already everybody knows this, but for my purposes, I would like to give this very brief introduction. What we're talking about is these hybrid superconductor semiconductor structures, and it thanks to theory work that really started in 2000s and connected this back to 1937 at Majorana. We have been inspired to search for Majorana modes in these structures. And then one of the experiments, like I said, I'll be showing our data. So when I was a postdoc in Delft, we did this work in an indium antimonide nanowire. We found zero bias peaks inside an induced gap. that appeared at finite magnetic field. And of course, the promise of this is that this is not just a zero energy state, but it's also non-abelian. So a big component is to prove that property. And even beyond that, people have started imagining whole architectures, this colorful plot on the lower left. You can see people coming up with schemes to make a topological quantum computer. So let me, you will now all see a poll question. It's one question that I would like you to answer, please, pretty much right away in the next few minutes, because we're going to have another question later in the talk. So let's, let's make it a little more interactive. So while I'm introducing the properties of Majoranas, if you could please answer this poll, that would be great. Okay, so we've been doing a lot of these Majorana experiments, and to summarize, it's mostly been tunneling, transport, and even in this tunneling, well, people here talk a lot about other signatures of Majorana in other types of measurements like Josephson and even more advanced setups. But even in just tunneling from normal to superconductor, you can establish Majoranas pretty firmly. And what you need to do is demonstrate several properties. And so if you see these properties, then there is not so much doubt that you have found Majorana. So zero bias spectral feature, so Majorana pinned to zero energy. Then, there's a theory prediction that it should exist in a very specific phase diagram. So you need to tune the chemical potential and apply magnetic field, but not just go to a field and search for Majorana, but once you found the zero bias peak, you have to explore and see that it exists in a region that is consistent with some kind of model. The simplest model would be just a kind of a square root dependence phase diagram that I will show, but more advanced models predict more nuanced regions, but it is always some region that should make sense. Then spin-orbit interaction is a crucial ingredient, so the role of spin-orbit should be demonstrated. For example, if you rotate magnetic field, a zero bias peak may come and go depending on whether you are aligned with spin-orbit or perpendicular to spin-orbit anisotropy direction in your structure. And of course, Majoranas come in pairs. It is kind of a fermionic mode that's split in two, and you need to establish this property directly. And there are some other signatures, the peak height has been talked a lot about, of course, the quantized 2e² peak height. So let's, so I see 16 people participated, and there's still like 60 people that could vote. So please vote. Voting is important. Well, maybe not in your countries. In our country here, voting is very important. And so I hope that you take 1 second to vote. And
sorry, Sergey, where is the poll? Where is the poll? How do we do it? I don't see.
Oh, you don't see it? I think everybody should see it on their screen. I don't know, click around.
I see it.
17 people see it.
I see it.
Can we get to 20 people in the next 5 seconds?
Easy.
Some people don't see it. Oh.
Yes.
It's like a pop-up window in your screen.
Maybe you're.
Okay. No.
Yeah, it's a separate window.
It's a separate window.
No, many people don't see Paul. Okay, well, I will click around, guys. Maybe you'll find it. I will keep going, okay?
Okay.
Okay, so this is one of our experiments that we've done in Pittsburgh. It's already a few years old, but here in the middle, horizontal line in the SEM picture is an indium antimonide nanowire. It's amazing material with high mobility, strong spin orbit, large G factor. Yeah, so on the right, we have niobium tinitride, which is a superconductor. And on the left, we have palladium, which is a normal metal. And underneath, we have these electrostatic contacts that are gates. So FG gates set up the tunnel barrier between normal and superconducting, and BG gates tune the chemical potential. So we tuned one of the BG gates, BG1, and we take these colorful maps, which are conductance maps. And if you look in the middle in the red frame at minus 0.42 volts on the BG1, we have this feature where a gap is closing, and then a zero bias peak appears at finite magnetic field, about a few hundred millitesla. And okay, this superconductor was the original choice. It gives a softer gap, but it has a high critical field, so it has pros and cons. I would say for topological quantum computing, certainly not a good choice because of the soft gap. But for looking at these spectral features, it doesn't really matter. So it's a decent choice. So when you plot the onset fields of zero bias peaks at different gates and the onset gates of zero bias peaks for different fields, well, you can see that they form this shape. And it's comparable to this red square root shape that is a theory plot from the most simple basic theory. And there is a bit of an offset, which could be due to finite size. But the point is, to the right of all these dots, it's all zero bias peaks. It is kind of a region in space with zero bias peaks. So that's what I was talking about zero bias peak being confined to a certain range. So you want to see that when you study Majoranas. You want to see such a region in parameter space that it makes sense in terms of Zeeman energy, induced gap, chemical potential, that corresponds to some kind of Majorana model. Okay, so people still cannot find the poll. That's a pity. There is kind of a, on the bottom of your window, a bar that says polls with a little icon with polls and little bars. So maybe click that. Okay, no icon. Okay, well, I have the icon. Okay, let's move on. So that was the phase diagram. Now, Majorana peaks are supposed to be quantized. So the peak height is supposed to be 2e squared over h. And originally, we put in the paper figures peak heights that were very, very small because the theorists did not properly inform us that that's extremely important to have a tall peak. So that's really a failure on the theoretical community's part. Okay, we actually had taller peaks even back in 2012. But here now we said, well, it's so important, let's look for it. So we found some peaks that go up in height and reach the right value. So here in panel A and B, you can see line traces in magnetic field where zero bias conductance reaches the value of 2e squared over h. And then in the middle column, we scan the tunnel barrier gate, and we see a kind of a region where 2e squared over h is a point where the peak lingers for some range of tunneling parameter, making kind of a plateau. So the right peak height can be obtained in these indium antimonide niobium tinitride devices, very similar to what I showed you. And then on the right column, we show this spin orbit anisotropy, right? Spin orbit has to play a role in inducing these Majoranas. And so you see that the 2e squared over h value and the peak itself is confined to a very narrow range of magnetic field angles, while superconductivity can be induced for any field orientation, and niobium tinitride don't care about the field orientation. But zero bias peak appears at 0 degrees, which is along the nanowire, which is where we expected from previous experiments where we independently established spin-orbit interaction. Okay, so this is all good. And now finally, this is kind of a fresh data, somewhat fresh, correlation, right? So can we observe zero bias peaks on 2 ends of the same device, of the same nanowire? So this is something we posted on arXiv a few months ago. Yes, we can see zero bias peaks on 2 ends of the device. So in this case, we have a superconductor in the middle and 2 contacts, left and right normal, normal 1, normal 2, or normal left, normal right. So we can measure 2 currents flowing to the left and to the right, and those are the 2 diagrams, G1 and G2. The bluer one is on the left and the redder one is on the right. And at a field of about half a Tesla, on both sides, we see the appearance of zero bias peaks at the same field in the same device. So this is the correlation of zero bias peaks. And this is something Majoranas should have. They should have such a correlation. Okay. So let's see. Well, so, you know, all these signatures of Majoranas can be demonstrated. Correlation, spin orbit interaction, phase diagram, zero bias peak and its height. They can all be demonstrated. Yes, so Kirill writes that these peaks are not really, well, they are at 0. There may be some instrumental offset. They are really at 0, but he also says the height is not 2 squared over h. Yes, that's right. In this regime, it's not 2 squared over h. So obviously, we still have some work to do. We need to have 2 squared over h peaks on 2 sides, but already correlated peaks is something. And okay, so where this is all going? Well, we want to make qubits, right? And so, okay, we're not quite ready yet to make qubits, but we can already start thinking about qubits, and there were many interesting schemes proposed. And like I said, I'll be just showing our work, but there is a lot of great work, especially on these architectures. Elsa, I will answer your question in a few minutes. The answer is coming. Yeah, so this is our scheme. We call it Brydonium, and well, it's a very complicated experiment. It is very hard to do. So in addition to our expertise in material science and mesoscopic physics and superconductors and semiconductors, now we have to add qubits into the same mixture. So the middle element here is fluxonium, which is a qubit that will read out the Majorana qubit. Majorana braiding ring is this dark black ring of superconductor where we have to perform braiding operations, and then we have to embed it in advanced circuit QED architecture, basically. And that's a big overhead, but nevertheless, it works. So these clock-like looking diagrams show that by coupling and decoupling Majoranas around the T-junction, in this case, our scheme involves flux, Josephson effect, 4-pi Josephson effect coupling. We can braid these Majoranas, but this braiding is not very topologically protected because all the Majoranas are coupled at all times. And so, you know, there is a certain window during which you can braid. So this is not really a good qubit for large scaling or memory, whatever. But it is maybe a nice scheme to demonstrate braiding, as good as other schemes, let's say, as difficult as other schemes. Okay, so that's the optimistic part. And well, thanks to all who were able to participate in the poll. And I was trying really hard to vouch for Majoranas in this first part. But I wasn't very successful. So now I stop the poll and I share results. And do you see the results?
Yes,
okay.
I see them.
No, no.
What a pity.
No, the ones who cannot vote cannot see
see the poll.
Well, we really need, you know, voting equity in this. Not every person can vote, apparently.
I think it depends on the Zoom version that you have installed, or whether you are using the web version or the client. I don't know. Anyway.
Okay. Well, so I see that quite a few people did not see it, but okay, let me tell you the results. So significant evidence for Majorana modes has been obtained. 2 votes, 2 people. And the other answer, Majorana zero modes have not been observed, 19. So 90% of those who were able to vote think that Majorana zero modes have not been observed. Despite my effort to convince you otherwise. Well, actually, I agree with the majority. Majorana modes have not been observed, I think, in this material. And now let me show you why. Let me first see if there are any questions. Andreas, yeah?
There are people voting through the chat also, but anyway.
Yeah, there is a couple of no votes in the chat, I also see. Probably, Yelena says yes. I don't know if she means yes, Majorana modes have been observed, or yes, she can see the poll. Probably she can see the poll.
Francesco Bortoi, yes, also.
No, but this is after I said, can you see the poll? So anyways, well, so there were a couple questions about correlated zero bias peaks, whether the appearances are statistically significant and whether they're correlated for all the right parameters, right, within the phase diagram and so on. So I will address that in a moment. Great. Okay, so you've already seen this slide with the signatures from transport, and I told you that if you see these things, there will be little doubt that it's Majorana. And I meant it. I meant this. I meant it, but I also left out one phrase at the bottom, which you see in yellow now, that they have to all be demonstrated in the same experiment, in the same device, and in the same parameter range, right? So I was doing a bit of, I was tricking you. I was showing you experiments from different years and different devices. And sometimes people show experiments from different labs that show one signature here, one signature there. You know, with all the control knobs and the gates and different materials, sure, you can, you know, and with all the devices that we measure, sure, you can measure 100 devices and find one with a one signature, but then it wouldn't have the others. So that's what allows these alternative explanations to, you know, survive. We cannot eliminate them so far. And what is this all about? Well, I think, I'm sorry, I wasn't really able to hear the talks because I am actually in Pittsburgh and it is very early here. But I suspect there were many talks that talked about Andreev bound states and maybe partially separated Majoranas. And so the physics here is basically what you see on the screen. So what we want is these well-separated Majoranas, which is the top picture, but maybe we cannot get that, so we might be happy with these partially separated Majoranas, and we would already be, you know, celebrating success. But there's also these completely trivial Andreev bound states, which is the bottom picture, where you can do this trick of decomposing it into Majorana bases, which I love. I think it's a wonderful theoretical tool to decompose bound states in the Andreev bases. But then the decomposition gives two identical wave functions. So it's completely trivial, right? And there is a continuum, but they don't fully match. And that's all very interesting physics. So Kirill writes that even if we show all the signatures, it would be not enough. Yeah, so I think it would be enough to prove we have this Majorana zero mode that you see on your screen on top. I think we can prove that with just transport. And we can, because it's a simple measurement technique, well characterized, gives a lot of evidence. And then I like to think about the non-abelian feature as a separate property. In fact, there may be other pieces of physics in between. So creating the right band structure in a nanowire and separating Majorana wave functions may be possible. There may be other physics that prevents us from proving that it's non-abelian, or maybe it's not even non-abelian. Maybe the approximation in which all the non-abelian stuff is derived is false. So that's a separate hypothesis, right? So I always argue strongly that you cannot wait for the non-abelian demonstration to convince yourself that you can split an Andreev bound states into two Majoranas. First of all, that's too long a wait. Second of all, they're separate features. They're separate properties. Okay. To me, as an experimentalist, they're separate properties. In theory, when you write the theory, they all come together. But you know, the theory is derived in some approximation. Okay. So now let me show you some more stuff that we see in our devices. So for example, here's a device just like what I showed you for the phase diagram, or actually for the correlated device, because there's actually another electrode on the left that we don't show in this SEM picture. Oh yeah, we can change the gate and we can see zero bias peaks. So that's the middle column with magnetic field dependencies. We can see zero bias peak. We can see zero bias oscillations. So peak coming and going, splitting and coming together. And we can see a very long peak that goes for hundreds of millitesla, almost a Tesla. Inside this soft gap, again, yes, the gap is soft, but you can see very clearly the peak inside the gap. Well, can you? In fact, it could be also a mishmash of several different peaks that come together near the gap, near the zero bias, right? So for example, the middle panel, the center of the slide, it looks like there's the state crossing, which is red, and then another one, which is white, displaced by a few hundred millitesla, and they together make it look like it's an oscillation, right? Okay, so okay, well, I don't know if we're gonna do the poll again because the result was so overwhelming. But it's nice to do polls and to interact during these conferences, right? It's much nicer than listening for hours one way. Okay, so at the bottom, we have these gate dependencies, right? So remember, in gate versus field, it should look like this square root nice region of phase diagram if it's Majorana. Well, here I sweep the gate in a slightly larger range, and we see all kinds of things crossing the gap. So at zero magnetic field, which is the top long panel, at zero magnetic field, there are states crossing, and we're now studying them very actively, what these states come from. They're very interesting. So we have an upcoming paper that will be on arXiv hopefully soon. They're crossing the gap, but they're not sticking at the gap. They're just crossing. And then when we apply magnetic field at 0.3 Tesla in this case, so that's the bottom panel, we have all kinds of regions where zero bias peaks form, seemingly independent of these crossing states. They just pop up everywhere. And when we zoom in, we see that this is a kind of a soup of Andreev bound states that is ubiquitous, right? This paper is called Ubiquitous Zero Bias Peaks because it's very easy to find. And Majorana should be a little bit difficult to find. We should be at the bottom of when the next subband enters the chemical potential, reaches the Fermi level, right? And then the next subband is spaced by some energy, which could be millivolts. So you should require some tuning to get to the next subband and see the next region of zero bias peaks. Well, in this device is not the case. The zero bias peaks are kind of everywhere. Why is the appearance of zero bias peak never correlated to closing and reopening of the gap? Yeah, so this is closing and reopening of the topological gap is another signature that would be nice to see, and I could add it to the list on my signature slide. Absolutely. Then why is it not seen? Well, maybe because we've never reached the true topological regime in these wires, or maybe because it's not visible because it's in the middle of the bulk, as some theories suggest. Okay, so there's another question. Tunneling transport experiments limited to tunnel coupling. Saclay people say that we are already at 1 gigahertz line width. Yeah, so that's not good for qubits. Yeah, within 2 gigahertz or 2 microvolts, we won't be able to say if we have 2 peaks or 1 peak. Fine. When we get to that, I'll worry about it. I mean, at that point, I will put this device in a resonator and crank up the, quality factor of the measurement to see if the peak is really a zero bias to within 1 microvolt. And at that point, I would be probably working with very, very long wires, multi-micron wires. Now I'm working with hundreds of nanometers. Yeah, so then Christian says, here it looks like the gap closes as ZBP appears. Okay, so there's a lot of interest in closing and reopening of the gap. So what I believe, and I think Jay Sao told me this, he was the person who articulated it to me the clearest, is when sharp resonances go to 0, that's not gap closing. That's just a state moving to 0 bias. You have to have a large amount of states all going to 0. So when it's a large bias window of conductance that kind of avalanches down to 0, touches, and then reopens. So inside this crossing is nothing, and above the crossing there's a lot of current. That would be gap closing. This is just an Andreev bound state coming to 0 and then crossing and going through. That's what I think. Yes, in fact, in this device we believe we have kind of a quantum dot, not really with Coulomb energy because it's all screened by the superconductor, but it's multiple dots, at least 3 or 4 dots in this device. That's the physics here. Okay, don't keep track of the time. I'm probably out of time. But here is the answer to the correlation.
You still have time.
Huh?
Yeah, you still have some time because we started later, so.
Okay, a little bit of time, okay. Well, I don't have any ambition to reach any point. I'm happy to have any discussion that people want. Okay, so here's the reveal of the correlation puzzle, right? The correlation I showed you of the zero bias peaks is accidental. It's the yellow point on the right. So for a certain gate voltage, the peak onset value is really exactly the same. And then you change around, you see that in general, they're not correlated. And in fact, there are examples where it's completely, completely different. Like there is no peak at all on one side and there is peak only on the other side. Here are some examples. Also, on the left, you see that when we have the quantized peak, right? You see on the left, we have on the left side, on the left of the slide, on the left side, we have this quantized zero bias peak. But when we look at the same time, on the right side, we don't see any zero bias peak. Okay, so when we have the 2e² peak on the left, where the red star is, on the right, where the yellow star is supposed to be, there is no zero bias peak. Okay, so 2e² quantization of the peak, or the value anyways, quantization is a big word, but 2e² value of the peak does not tell you anything by itself. And this is an experimental statement now, right? Because we've seen some nice theory work saying the same thing, but it's important that this is now shown also experimentally in a separate experiment. Okay, so what do I think is we need to do here? So the good news is that we know all this now, and it's the first important step is to be honest about what we've achieved so far. And like the poll suggests, it looks like most of the audience believes there is no evidence of Majorana. That's important to realize that there is no evidence yet of Majorana. Then the second important thing is to realize that the things that look like Majorana is a remarkable situation in physics when so many signatures of something so dramatic can be something else. So all these Andreev states are closely related to Majorana, but they are pretty good at imitating Majorana. So, but now we know what they are and where they come from. So we are, you know, information is power and weapon. So we can use it against these states to kind of shuffle them around, eliminate them, and maybe find the Majorana. But we also need better materials. So to eliminate Andreev states, to make it more pure and make it easier to see Majoranas, we need better materials. That's easy to understand, right? It's easy to understand that the cleaner the nanowire, you know, if we had 100,000 mobility nanowire or few 100,000, that would be amazing because we would have a mean free path of a micron and our life would be easier. But there are other more subtle things, and some of the theorists in the audience here, like Yelena and others, I think also the Spanish folks, Ramon and Elsa, have pointed out that, and also the Maryland people, you know, everybody pointed out that, you know, maybe the superconductor is too strongly coupled to the semiconductor, and the electron that we're dealing with is not actually an indium antimonide electron. It is an aluminum electron or a niobium electron. So maybe we need to create some kind of tunnel barrier between the superconductor and the semiconductor and control it, tune it, so that we decouple the semiconductor from the superconductor, and perhaps that would allow us to, you know, also reduce the number of subbands that we work with, because now from all these multiple quantum dots, our modeling shows that it's probably tens of subbands that we have under this superconductor. And that's just too much to clearly see Majorana. Okay, a lot of questions. Sorry, I was talking too much. Well, it is my talk. Okay, is there understanding why one gets quantum dots in these wires? I answered partially this question, right? So part of it is kind of disorder things, you know, surface during fabrication. But another part is just geometry, right? It's a complicated device. To measure two Majoranas, you have to put contacts on top, gates underneath. You know, contacts could be asymmetric. So just the geometry of the device can create confinement that we don't want. We don't think it's in our Hamiltonian, but it is. How long is the region in the middle? So for the correlation experiment, it's 400 nanometers. And remarkably, already that relatively short length gives uncorrelated signals on two sides, right? So if it's 200, it's kind of correlated. And then 400 already not correlated, right? So there was not even point to go to 600 at this point, right? So maybe with better materials, we can go to 600, 800, and so on. Hello. Okay, Juan Carlos, how big is spin orbit gap here? I don't know, I think it's the same as always. So it's maybe 100 microvolts. Number of subbands from experimental data, we can estimate it by fitting our this mishmash quantum dot data to a model. So that's done by Tudor Stănescu, and the model we developed with them has maybe 20 subbands. That kind of fits best the totality of our data. Okay, so let me just show you some of the things we're thinking in the materials space. So we've explored a couple of semiconductors like indium arsenide, indium antimonide, and a couple of superconductors like aluminum and niobium, but there's many more, and it's I find it very nice that finally people started producing different combinations. So this plot shows a kind of a universe in the super semi space. So on the bottom you have semiconductors, on top you have superconductors, and the lines are various things that were tried, and the diagram is somewhat old. Probably some lines have to be added. And so the idea is to find a combination, materials combination, that not only gives a nice interface in terms of crystal quality, but also optimal for Majorana. Maybe provides optimal coupling between metal and semiconductor. Maybe it optimizes spin orbit coupling. And a lot of important work is being done in this dimension of the problem. And there's new interesting possibilities opening up by adding magnetic materials. So to, maybe shift all this work to zero field. I think that would be very nice for the future, once we get to more advanced devices for sure. Okay, so I want to advertise one piece of work that we've done. There is work by others, like in Copenhagen, nice work on lead, which is similar. But here, we took again the indium antimonide wires, so you can see them standing up on the left. But then the chip also has some of them growing as flakes. So these triangles are flakes, also of indium antimonide. And so if you come in and you go with your beam of metal such that the flake shadows the wire, then half of the wire will have metal. On top we have tin, and the bottom wire will be uncovered. So this is kind of a shadowing trick, one of several that have been recently introduced. But the idea is that this entire interface of superconductor semiconductors created inside the MBE reactor, or after maybe the wire came from somewhere else, but then it was carefully cleaned in a well-controlled process. And this gives good results, hard gap that survives to large magnetic fields. And also interestingly, this tin that we use in this work is not epitaxial. So one of the strong beliefs, I think, was that it has to be epitaxially matched, otherwise hard gap is not possible. Or hard gap is possible. We still may want epitaxial matching for more advanced devices. I don't know, for qubits, we may still want that. But for hard gap, it's not necessary. And it was even possible to demonstrate this coveted 2E charging effect, which was previously only seen in aluminum, perhaps for the lack of trying, but nevertheless, it is kind of a landmark for, should be for any superconductor, that you have a small island of superconductor, you put Cooper pairs on it, it should be advantageous to put 2 electrons on it rather than 1, because you have to break Cooper pair and pay that energy. But so far, it's been only demonstrated in 1 superconductor, aluminum, but now we have it in tin. And this is an important property also, perhaps, for qubits. Now, back to qubits, and I'm about done. Like I said, this is quite futuristic, even if we were working full speed. But also our efforts to make qubits were impeded by the global crisis, which is the pandemic. And for a while we were sitting at home, not being able to use the lab. But fortunately, we were able to use an existing quantum computer, okay, at IBM. And so we decided to do braiding on an IBM quantum computer. what we used is we used the Jordan-Wigner transformation to map the Kitaev model onto spins, onto an Ising model. And, you know, quantum computer at IBM is a bunch of spins coupled. So you can encode the transverse Ising model. And you can come up with a sequence of pulses for 3 qubits that perform braiding. And this sequence of pulses, you have it on the screen here. Well, this is only 1/6 of braiding. So 1/6 of braiding is taking 2 Majoranas and swapping, sort of coupling 2 Majoranas together, right? So then you have to do it 6 times. And after that procedure, you've braided. Why do I only show you 1/6 of the process? That's because we couldn't do a longer process because gate fidelity that we need, that we have only allows us that. So a 2-qubit error rate at IBM is 1%. And so that means that we can only run about, well, really 25, 30 CNOT gates before the outcome of the quantum simulation is 50-50 between what you want and what you don't want. So with this 1/6, we got some encouraging results. So we were targeting the state 000, which means that the Majoranas have been swapped. And it is the highest probability result. But you can see there's a lot of weight in all the other results. Okay, so why do I show you this? Well, it tells me that we certainly need better quantum computers. And so there is perhaps room for Majorana in all this still. The race is not fully set, but it is also fun. It is fun to play with this Jordan-Wigner transformation, and there's a lot of things that can be tried. So since the poll was so overwhelming, I don't know if we should run it again. Maybe just for fun, I will restart the poll. And let's see, we had 2 to 19, actually 2 to 20, because at least one person voted. So we had 90%. Let's see what we have now. So you should see the poll again. And I apologize to those of you who don't. But the poll is, yes, significant evidence for Majorana modes has been obtained, or no, Majorana modes have not been observed. So you can also vote in chat. And let me read some of the questions. I think there's no new questions. Great. I'm sorry if I missed any question. You can maybe ask it again or point to me if I missed.
So
certainly fun.
Yeah, I was going to say that if you want to unmute your microphones, please feel free, because this is just the last minutes of this talk and this morning session. And if you want to, if we can hear your voice, it can be nice.
Hi, Sergey, it's Yuval.
Yuval, hi.
Hi. So in this Jordan-Wigner transformation, there is this string operator, which is unlike the local Majoranas. So how you deal with that? I mean, I'm not sure that braiding will be exactly the same as in the Majorana wire when they are local.
Yeah, so it is not, so I think we're doing this T-junction with 6 Majoranas, right? Well, actually, it's only 3 qubits. And each qubit is like 2 Majoranas.
No, that's I understand, but you mentioned something with Jordan-Wigner transformation.
Yeah. So it is not topologically protected. So I think when you couple and decouple, you lose those strings, right?
Right. Yeah.
You lose the strings.
It's not expected
it is
to
not,
be
and the transformation loses topological protection.
Right. Yeah.
You're right. Yeah. So this is just, this is a COVID project, right?
I see. Okay.
And if you can also put your cameras on so we see you, because we will take a photo soon. And that would be great.
A conference photo?
Yes.
Yes, you should be able to switch on your cameras. You are allowed now. So.
Okay, so we have 26 people voted. If anyone else is able to vote or share your opinion, please go ahead. 27. Can we get to 30 now?
Unfortunately, I think we should go out from the talk and then come back maybe to have the poll.
Okay, well, don't do that, please.
But I think it's too complicated.
It shouldn't be necessary, actually, because we did it, Sergey and I did it while the other speaker was talking, and we didn't go out, so.
Okay.
We created the poll. So anyway, I guess it's a question of the Zoom version that we have installed.
Okay, so let me then tell you the results. Let me stop the poll. We had it running for 3 minutes. 28 people participated. So more participated now. Thank you. And the results are that now 26 people, 93%, say that Majorana modes have not been observed. Interestingly, still 2 people, maybe the same people, same 2 people, say that significant evidence has been observed. So, well, if I'm in social sciences, I would say that my talk had a 3% effect. Which, okay, I just need to give like 30 more talks and we are there, right?
Yeah, perhaps it would be interesting to see why these people think there is enough evidence.
Well, I don't want to put anyone on the spot,
yes.
but you know, I think if we run this experiment in a more general session with not so many experts, we would probably have a more dramatic effect.
Yeah, I agree.
Maybe before and after, right? So that would be interesting to do at some point in our life. Or maybe we'll find the evidence and then it will be all good.
I mean, let's hope we can measure Majoranas in this system, no? I mean, that would be the ideal thing. I think we all want that.
We're working on it, yeah. You know, it's more than hope, but you have to be realistic about what you have right now.
Okay. So, people, thank you very much, Sergey. Wonderful talk, and thanks to all the speakers in this morning and all the participants. Thank you very much for your questions, because it's not that easy that people, take the courage to ask, apparently. So thank you really very much. And let's take a photo. So please connect your...
We have done, maybe some people didn't attend the other sessions. What we do is to put everybody in gallery mode with the cameras on, and we just take screenshots. Everyone takes screenshots in their computers, and then maybe you send me a few pictures, because not everybody can fit in the same screen. So this way, hopefully, we have different pictures. Okay.
Yeah.
So we do a few screenshots.
Probably should smile.
Yeah, we smile.
Proof that we were here.
Right. So while you take pictures, let me remind you about the afternoon session at 5 p.m. Yesterday, we had a very, very nice experience with this afternoon session. We created these discussion rooms in Zoom, and this is a very useful tool, actually. So we have different discussion rooms with different abstracts and people, and it became actually a very lively, live discussion. I mean, we end up very, very late, actually. We were discussing until, I don't know, 8:30 or something. So it was very nice, actually.
Yeah.
So please join us this afternoon, and thank you for coming. It's been a great conference so far.
I will join them.
Thank you, everybody.
Bye.
Hopefully next time we can do it in real life.
Yes.
Will you upload the session somewhere? The video of the session?
we are recording all the sessions. We are still waiting for some consents, to put it online, because we need the agreement of all the speakers of the session to put it online. But we have the recordings. So okay. I guess everybody agrees, and we are still waiting for some people. But I guess it's just they forgot to send the agreement. Okay. So at some point I will send you a link or something, or the main organization will send you a link with the videos.
Okay. Thanks.
Okay. Thank you.
Thank
See you
you,
later.
everybody.
And also don't forget to attend the invited sessions. They are very, today, for instance, the semi-plenary is Hélène Bouchia, who probably most of you know. She will be talking about also this, this topological, crystalline topological insulator. So it's going to be a very interesting talk for sure. See you later.
Thanks. Bye.
Bye.
Bye.